start sharing screen. Let's see. Share screen. Desktop 2. Okay. So I will also share my desktop, my PowerPoint. 1 second, please. Let me arrange this around. Oh, wrong slide. So, let's see. I will also need to open up my chat. 1 second. I'm trying to find my chat. So here's the plan. The way I'm going to do it is if y'all have any questions, you can stop me at any time. Feel free to speak up. You can either speak up or you can message the chat window. Yeah, but I might not see your chat window immediately. So if that's the case, yeah, and you really need to stop. You are welcome to chat. You just speak up. Okay, so this is 5907 pattern recognition, right? And the first half of this course is also 5027. Okay. Oh, why is it not moving? So, oh yeah, one thing I should mention is that sometimes it has happened to me once. I got disconnected from the internet. Not to worry, I will try to reconnect as soon as possible. You just stay in the Zoom room, and once my internet comes back, I will be able to rejoin. Okay. So anyway, can everyone see my share screen? No problem, right? Awesome. Okay. So anyway, I'm Thomas Yeo. I'm the lecturer for 5907. So 5907 is split into 2 halves. Okay. I will teach the first half, and I'll cover topics including Bayesian decision theory, parameter estimation, supervised learning, and non-parametric techniques. So this first half is equivalent to 5027. So the second half will cover unsupervised and supervised dimensionality reduction, clustering and application, and a bit of deep learning. Now, so this year usually is taught by Dr. Feng Jiashi, but due to some sudden change, his course load is now split among 3 people. Robbie, Mike, and Xingchao. Okay, they're all excellent teachers, so I'm sure that you're in good hands. Okay. So, yeah, so this is roughly the rough schedule for the next 6 weeks. Okay, so let's see. The lecture is today, since you're here, you're at the right place, 6 p.m. to 9 p.m. It's done by Zoom, and the lecture is being recorded, so it will automatically be uploaded onto the Luminous in a few hours or next day. I'm not sure, but I would appreciate it if if y'all can still attend the module during the Zoom session to at least keep company. Okay, so in terms of office hours, I'm happy to stay behind after the lecture and talk and answer any questions you have until the last person leaves. Okay. For the second half of the semester is by appointment only. So there will be 2 GA for this course. Oh, sorry. The first half of this course, so the 5027 and first half of 5907, it'll be handled by Leon and Xiaoxuan. These are their email address. They will hold office hours on Monday, 6 p.m. to 7 p.m. by Zoom. So this is the Zoom information. Okay. So I guess you can ignore this because this class is oversubscribed. So it's unlikely we will accept any more students. There are actually already 200 students in the class. Yeah. So there are 3 optional textbooks for this class. Pattern recognition by Duda and Hart, machine learning, a probabilistic perspective by Kevin Murphy, and computer vision. Okay. So this book on the right can be downloaded for free. Okay. Yeah. Okay. So in this course, I'm going to assume that you're familiar with probability, statistics, and linear algebra. So I'm also going to assume that you're familiar with either MATLAB or Python or standard languages like C, C++. Basically, for the programming assignment, you're expected to use either Python or MATLAB for programming. And I guess it's up to you what to use. But in this class, we won't actually be covering the, what do you call it? How to program, okay? So basically, you'll find this class very hard if you don't have the prerequisite, right? And I know some of you are undergraduate students. So just to give you a warning, you will also find, if this is a first graduate class, you'll find that it's very hard as well, okay? Does anyone have any questions so far? Okay, I'll continue. So the class does not cover state of the art, but we hope to teach you concepts that you can use to understand state of the art. Obviously, for state of the art stuff, you can, I mean, the best ways are to go for like conference papers or journal papers, right? And in the 6733, advanced topics on vision machine learning, it's a seminar class where you read papers from conferences and journals. That's also a deep learning course. I believe that the current course is a prerequisite for the deep learning course. Okay. So each week, as I said, I'll post lecture slides on Luminous. You can see that there are actually two versions. There is a condensed version as well as a version with detailed notes. So with this detailed notes, if you sometimes did not hear what I say in class, and you're of course welcome to clarify in class, but if you missed it, you can go back to the detailed notes and you can take a look at that. You all know what I'm saying? So the detailed notes is, hold on 1 second. So I'm still, right? So you can see that there are detailed notes at the bottom, right? Especially for the math part, you might find it helpful. Okay. Okay. So where was I? Okay. So each week I will also give you some problems to solve. The first assignment has already been posted. The assignment will not be graded, but I really strongly recommend that you try to do it. I will post the solutions the next week. And if I have time, I will go through solutions from the previous week's lecture. Okay. So yeah, so as I said, you know, they won't be graded, but please try to do them because I believe that you will understand the material better. So there are two continuous assessments. So basically there are two programming projects, each worth 20%. And the final exam is worth 60%. This is for 5907. For 5027, you have one programming assignment is worth 40%, and it's the same as the 5907 CA1. Okay, and your final exam is worth 60%. Okay, so for both of this, more information is to come, but basically, from what I know, both will be virtual. Okay, both will be virtual. Okay, does anyone have any questions so far? You're welcome to unmute yourself and speak up. I believe that you all have the power to unmute yourself, I think.
Yes.
Yes, cool. Do you have a question?
No, I just wanted to acknowledge. Thanks.
Okay, sure. Thank you. I like participation. It's fun. Yeah. Okay. Thanks. Yeah. Okay. So, oh, someone just asked me, will the final exam be offline? Wait, I cannot tell if did I. So the final exam will be virtual. Will be online. Is that what you're saying? Did I answer your question? Knitting. Yes. Yeah. It'll be online. Yeah. Okay. So on week 3, we will hand out CA1. And CA1 will be due the Monday after recess week. So CA1 is worth 20% of your grades for 5907 and 40% of your grades for 5027. Okay. And basically it will cover lectures 3 to 5. And there are basically 4 sections. And my thinking is that the lectures kind of teach you more theoretical concepts. And then the ungraded homework helps you understand the theoretical concepts better. And then CA1 essentially lets you implement these theoretical concepts. Okay. I would suggest when you have the assignment not to wait. So you're given basically from week 3, right? So week 3, week 4, week 5, week 6, and then you have recess week. So technically you have 5 weeks, but I'll suggest you don't wait. Some students find it very easy, some students find it very hard, right? Okay, so according to previous year's survey, the minimum is 5 hours, and then the maximum is 120 hours. So basically, is a huge divergence across people. Okay. Okay. All right. Does anyone have any questions? Okay. So none. Oh, do their final exam includes coding? I'm not sure yet since I've not set the final exam. Why don't you ask me closer to the date? Yeah. Any other questions? Okay. None. Okay. Sure. Okay. So let's start. Yeah. Hey, Xin Chao. Hey.
You didn't mention about the second assignment, right? I mean, when will the second assignment be?
The second assignment will be in the second half of the semester. Yeah. And frankly, Xin Chao is up to you since Xin Chao is teaching the second half. Yeah. Yeah.
All right. Okay. Thanks so much. Okay.
Yes. You want to tell the students when you want the second assignment to be?
I don't know yet.
Why are you asking me?
I thought you have a kidding. Yeah. Okay.
I mean, I certainly hope that I have you should have complete say in your half. Yeah.
Yeah.
Anyway. All right. Okay. So thanks for joining us, Xin Chao.
Yeah, I mean,
okay.
Thank you for interrupting you.
So anyway, so this is an introduction. So as you probably know, artificial intelligence is intelligence displayed by machines instead of humans. This is something that computer scientists have been trying to achieve since the 1950s. These efforts have largely failed, but in the last few years, there's a lot of interest because of impressive results from researchers at University of Toronto and companies like DeepMind. So, and this resurgence is made possible with machine learning. So basically, in this class is called pattern recognition, right? But we kind of use the term pattern recognition and machine learning interchangeably. Obviously, there's some slight differences, and some textbooks do make a big deal of the difference. But for the purpose of this class, I say screw it. Let's treat them, as the same thing. Okay. So basically, the goal of pattern recognition is to automatically detect patterns from data. And in the case of machine learning, the goal is to learn from data without being explicitly programmed. Okay. And there are many real-life applications of machine learning. So according to Microsoft, 97% of emails are spam. So without automatically filtering these spam emails, communications by email will be impossible. And frankly, I'm not sure if you have noticed, but actually I've been getting a lot of more spam emails nowadays. So it seems like we're losing this war on spam. So yeah, anyway. So in addition, it's used in speech recognition, such as in apps such as Siri, right? We can use machine learning to recognize handwritten digits. This allows post office to automatically sort millions and billions of physical mail, and to automatically decide where the physical mail is going based on the zip code. So Google search relies on machine learning. So are driverless cars. Although, as if you've read the news, you hear that actually driverless cars are not doing so well. So it seems like we're a bit further away from having true driverless cars as we thought. Machine learning is also useful for detecting, for example, banking fraud. A lot of people are actively working on using machine learning to detect and to diagnose disease, and perhaps to predict what kind of treatment might be better for you as a patient. Yeah, I mean, I can go on and on, but here's a kind of a demo from Google. Let me see.
Google. Book a table for 2 at El Cocotero on Tuesday at 7.
All right, just in case that's not available, can I try between 7 p.m. and 8 p.m.?
Sure.
All right, I'll call to book under your name and phone number, and I'll update you in the next 15 minutes. Is that okay?
Perfect, thanks.
Cocotero, how may I help you?
Hi, I'm the Google Assistant calling to make a reservation for a client. This automated call will be recorded. Can I book a table for Tuesday the 12th?
Okay, cool. And how big is the party?
It's for 2 people.
Great. And when did you say they want to come in?
Tuesday at 7 p.m.
Okay, let me check. I don't have 7, but we can do 8.
Yeah, 8 p.m. is fine.
Perfect. And can I get their name?
First name is Anna.
Okay. We'll see you on a Tuesday. Thank you.
Okay, awesome. Thanks a lot.
Cool. So basically, applications like this would basically not be possible without kind of modern machine learning. And but as you can see, you can also see the limitations. As you can see that these kinds of applications are not very widely used, and that's because as of right now, the use of this kind of natural language processing, this kind of applications are still extremely limited to very narrow domains. Okay, so does anyone have any questions before I discuss various types of machine learning? Oh, did someone accidentally draw a line there? Is that me or? Okay. Okay. Don't accidentally annotate on the screen. Yes. Yeah. Okay. Okay. So okay, if there's no further questions, let me continue. We can basically divide machine learning into a few kinds. So the first type of machine learning is called supervised learning. Basically, we're given a training data set D, and D consists of n data points. Each data point consists of an input-output pair, xi and yi, So xi is the input and yi is the output. So our goal here is to learn the mapping from input x to the output y. So basically, we want to learn this function, y is equal to f of x, right? So in this case, D is the training set, right? And x can be basically anything. It can be images, emails, molecular shapes, and so on. And we typically represent x as a p-dimensional vector, which we can call features. So y is called the output or the target variable. And if y is discrete, this supervised learning problem is called classification. If y is continuous, then we call this regression. So for example, if we give the supervised learning algorithm a database, and this database consists of MRI images, right? And each MRI image is labeled as coming from either an Alzheimer's patient or a healthy participant, right? So the supervised learning algorithm will learn the relationship between the MRI image and the target labels. Okay, so in this case, the target labels is either Alzheimer's disease or healthy, right? So then given a new test image, the algorithm will try to predict whether the patient is healthy or has Alzheimer's disease, right? So here, I give you these 2 images. So let's say the top image, would you predict the person as being healthy or has Alzheimer's disease? So what do y'all think? Okay, so we have most people predict Alzheimer's disease, and that's correct because of you can see this part's called a ventricle. This large ventricle indicates that the brain is suffering from atrophy, and so you have these large ventricles. And you can see that the cortical gray matter is also thinning out, right? So this is a healthy participant. So you are doing very well, as good as the machine learning algorithm. So in unsupervised learning, our data set D consists of X, right, but no Y. So basically, they only have images. They only have features, feature vectors P, right? And there's no target label, right? So the goal here is to learn interesting structure in the data. So unsupervised learning is attractive because labeling the data can be very expensive. So for example, in supervised object detection, we need many training images where different objects are labels, right? Chairs, tables, cars, humans, right? This is very labor intensive and expensive. So it'd be nice if we can present images to the computer and the computer automatically discovers the object categories. Now, in other situation, it may be the case that we truly do not know what patterns or categories are in the data, right? So we want to automatically discover these patterns in the data, okay? So as a result, oftentimes unsupervised learning is quite tricky because it's more open-ended and there's no ground truth. And so validation is more difficult. And so typically people would need to come up with to make up some quantitative way of evaluating the algorithm, right? But a lot of time, because there's no ground truth, it's a bit hard. So for example, now I give you a bunch of MRI images, right? And we're supposed to discover something interesting from the data, right? So then what do? You could apply some unsupervised learning algorithm, right? And it might cluster these MRI images into two groups, right? So maybe this group and this group, right? And after we get these two clusters, we can then go in and we can try to study to see, what is a cluster, what did the algorithm discover, right? So in this case, for example, we realize, the algorithm has discovered, Alzheimer's patients versus healthy people, right? But there's no guarantee this will happen, right? Because this is an unsupervised learning algorithm. The algorithm may be dividing, let's say, old versus young, right? It can be dividing the images into male versus female, right? In some sense, it will be correct for the algorithms to do it, right? If one algorithm divide the images into Alzheimer's versus healthy, another algorithm divide the images into young versus old or male versus female, right? It's a bit hard to say which algorithm is correct, and that's why a lot of time it might be tricky to validate unsupervised learning algorithm. Okay. So to summarize, supervised learning is great if we know what we want to predict, and we can typically use unsupervised learning if we want to discover something new from the data, right? There's obviously other types of learning that we don't cover in the course, such as semi-supervised learning. So in this case, some data might have target labels, some data don't. And in reinforcement learning, there is an agent interacting with the environment, right? And the agent tries to learn from trial and error. So the agent will perform some action and in turn receive reward, which might not occur immediately, right? So for example, an example of reinforcement learning would be the animal foraging for food, right? So the animal is moving around, the food is the reward, but the reward might not come very frequently, okay? And of course, you might have heard of reinforcement learning because, for example, DeepMind developed these algorithms that can beat the world champion in Go. Okay. Does anyone have any questions before I continue?
Hello, Professor. I have a question. What's the difference between the supervised learning and the reinforcement way of learning? Because I see both method has some sort of if reinforcement provides sort of
supervision. Yes, you're right.
Yes.
Yes. So in some sense, yes. So I think you can think a little bit as for reinforcement learning that is essentially some form of supervised learning, except that it's a lot more dynamic, right? Because you have an agent that is performing action, and then you can get a delay reward. Yeah. But typically in the field, people separate these as separate problems, and the kind of algorithms can be quite different tackling these problems. Does that answer your question? Cool. Okay. So any other questions before I continue? Okay. So here's some background knowledge in machine learning. We're going to now discuss some background knowledge in machine learning. So basically designing a machine learning system often require the following steps, right? We have to collect the data we need to select features, and we need to choose the model, and we need to train the classifier on the training data. And then we need to validate the resulting classifier in the test set. Okay. And but for anyone who has done machine learning, a lot of time things does not work, right? And so you might realize that your results are not good, and so you need to go back and revisit some of these steps, right? And we might need to choose the different models. We might need to select different features, and in the worst case scenario, you even have to recollect your data because you did a poor job in collecting the data, right? So we're going to discuss kind of a toy example on supervised learning that illustrate this design cycle, right? Suppose we have a fish packing factory, right? And we want to automatically sort fish, right? And these fishes are coming in on conveyor belt, right? And we want to divide the fishes into salmon versus sea bass. Okay, so we can start by setting up the conveyor belt and cameras, capturing the images, and we're going to label the images as either salmons or sea bass, right? And then after that, we're going to do some pre-processing, right? Maybe we need to enhance the images. We need to remove the background. Maybe there's some fish on top of each other. This is called occlusion. We might need to separate occluding fish. And then we might extract the single fish, right? And then we can then use, apply the machine learning algorithm to the single fish to classify whether the fish is a salmon or a sea bass. So we might divide our data into training set and a test set, right? We can extract some features to be used in the classifier. Possible features include the length of the fish, the width of the fish, or the brightness of the fish, and so on, right? Once we settle on the features, right, we're going to train the classifier on a training set, and we're going to evaluate our performance on the test set. Okay, so importantly, this test set and the training set should not overlap at all. Okay. And maybe the results are terrible, and so we have to revisit the previous steps, right? As I was saying before. Okay. Does anyone have any questions so far? Okay, we can continue. So for example, right, maybe we start by testing if the length of the fish is good for differentiating between separating salmon and sea bass, right? So here's the histogram. So the black color histogram is salmon, the pink color histogram is sea bass, right? So let's say, and the x-axis is the length, right? And this is the number of fishes, right? The y-axis. So maybe we select a threshold, let's say L star. Let's say L star is decision boundary, is the optimum threshold that minimizes the number of errors, right? So basically below this L star, we classify fishes as salmon. Above this threshold, we classify fish as sea bass, right? And you can see that there is quite a lot of overlap. There's quite a lot of overlap between the histogram, right? So which means that there will have a bunch of mistakes. Okay, we have a lot of mistakes. So as I said before, this dotted line is called the decision boundary. Decision boundary means that on one side we'll classify as salmon, on the other side we'll classify as sea bass. Okay, and so maybe we should pick different features, right? So here, maybe instead of fish length, we can look at the lightness of the fish, right? So this is the histogram for the salmon. Again, this is the histogram for the sea bass. And you can see now the histogram don't overlap as much, which means that now if we use the decision boundary like X star, right, we can achieve a pretty low number of errors. Okay. Now, so does anyone have any questions so far? Okay. Now, just not talk about errors, right? But a lot of time, errors is not our most important criteria, right? So, for example, maybe customers, if the customers are buying sea bass, right, and they find salmon, then they'll be very upset. Oh wait, hold on, no, the other way around, right? So in this example, right, if you have so when they're trying to buy sea bass, they might be okay to get salmon, right? But if they're trying to buy salmon, they'll get very upset if they get sea bass, right? So as a result, one type of errors is worse than the other, and so we might want to shift the decision boundary, right? So if we shift this decision boundary to the left, right, we will essentially reduce the number of CBAS that's wrongly classified as salmon, right? Because you have a bunch of CBAS, right, that you are now correctly classified, right? Now you have this, you have more salmon. This, you see this black curve here. You have more salmon that are wrongly classified as sea bass, right? But that's not a problem because customers don't mind that, you know, that they're getting salmon when they're trying to buy sea bass. Okay. So in addition to lightness, we can try to add more features, right? Maybe we can consider width of the fish as a feature, right? So now with these two features, we can see now this is feature 1, this is feature 2, right? And the black dots are the salmon and the pink dots are the sea bass, right? You can see that with this linear decision boundary, we can actually separate salmon from sea bass even better, right? So basically by including width as a feature, we can get a lower error rate. Now, we have to be careful, of course, because even though more features can improve performance, sometimes the features are not useful. And if you have too many useless features, you might end up confusing the algorithm. Okay, so this is called the curse of dimensionality, where too many features can lead to worse performance. Okay, so generally speaking, if we have a fixed number of data samples, let's say n, right? In our example is the number of fish, right? So as we increase the number of features, right? The training error, this is the error in a training set, it will keep dropping, right? However, that might not be the case for the test set, which is the rate curve, right? As we increase the number of features, the test error, which is the rate curve, might drop at the beginning, right? But eventually, as we have too many features, the error will get worse. Okay. So the gap between the training and test error is called overfitting. Okay. So this is just a conceptual idea, right? And there are some recent work that have challenged this kind of curve. But for the purpose of this class, I suggest that as a basic, it's good to have this curve in mind. Okay, this picture in your mind. Okay. Now, instead of increasing the number of features, right, we can use more complex decision boundaries, right? So this means that essentially we are using more complex models, right? So instead of having a straight line, we can use a quadratic curve, right? So a straight line, equation for a straight line, for a linear straight line, there are less parameters than a quadratic curve, right? So in this case, by using a quadratic decision boundary, we actually reduce the number of errors. But if you have a model that's too complex, right? For example, you have this wiggly line, right? Then you might be overfitting to the data, right? So for example, so in this case, this wiggly line actually very cleanly separate the black dots from the pink dots, right? But imagine that we observe a new fish here where the question mark is, right? You know, according to this decision boundary, we should classify this as sea bass, but you know, this might be overfitting and this could actually be salmon. Okay. And so in generally speaking, roughly speaking, the model complexity is roughly related to the number of model parameters, right? So a quadratic decision boundary requires more parameters than a linear decision boundary. Okay. Someone, oh, sorry, let me finish this part first, right? So like before, suppose we have a fixed number of data samples, n, right? This would be the number of, for example, number of fish photos, right? So as we increase the number of model parameters, again, the training error would decrease. And then in this case, the test error might decrease and then increase. And again, the gap is called overfitting. Okay. Someone, Emil is asking, where is validation? Can you elaborate your question? Do you mean where's the validation set or something? Oh yes, we will talk about validation set later. In fact, I think in the next slide we'll talk about validation set. Yeah. Han Tai is asking how many features are considered too many. It really depends on the problem because if you're including good features, then actually you know you can keep adding and your performance might keep improving, right? But if your features are bad, even adding a few more might give you bad performance. Okay, does that make sense? So the number of features and the complexity of the model really depends on the particular problem you're trying to solve. Does that answer your question, Hantai? And Knitting is saying, does overlap of histogram always lead to errors? In this case, yes, in the sense that when you have, let's say you're using a particular feature X, right? If there's the histogram overlapping and we're using lightness as a feature, right? This means that and when you pick a particular threshold, the overlap parts are where the errors are. So yes, in general, if you visualize the feature and they're highly overlapping between your two classes, then this is not so good a feature. Okay. Okay, let's continue. So okay, so now to really test the quality of our algorithm, right? We need to evaluate the generalization error on the test set, right? But in general, if we split our data into a training set and a test set, is generally not enough, right? Because imagine that we train an algorithm on a training set, right? And the error is terrible in the test set, right? And then you're like, okay, obviously you're not going to give up, right? You're going to try with a different algorithm on the training set, and then now the error is slightly better in the test set, right? So you have already used the test set twice, and you repeat with another algorithm, and each time, you know, your performance actually improves, right? But after a while, you'll overfit to the test set. And so this is not a good practice. Okay. And so what typically people might do would be, for example, split the data into a training, validation, test set, right? So basically you train on the training set and then you evaluate your error on the validation set, right? And then you can repeat as many times as you want with different algorithms, different parameters, right? Until you're happy. And then only then do you then try to apply this to the test set to get a realistic error quantification. Emil is asking, but isn't the validation set same as the test set? No. So you want to make sure that the training, validation, test set do not overlap at all. So let's say you have 1,000 let's say you have 1,000 data samples. Maybe you put like 600 in a training set, 200 validation set, and 200 test set. Does that answer your question, Emil? Does anyone have any other questions as well? Okay. Oh, hold on. Dongxing is asking what? Okay, I think you need to type out a question and answer. Oh, does the validation set will be trained during repeat? So in general, training will occur on a training set. You will fit your parameters onto your training set, right? So for example, if you have a linear decision boundary, you will try to fit your linear decision boundary on your training set, and you're only using the validation set to see how well you're doing so far. Does that answer your question, Xiaofeng? What's the ratio of these three kinds of data set? There is no hard and fast rule, I think, in terms of this data, in terms of splitting this data set. Yeah, I mean, 80-10-10 is fine, but in general, the way to think about this is that you want your training set to be as big as possible, right? Because the bigger your training set, you know, the more complex model you can fit, right? But on the other hand, for the validation and test set, you don't want that to be too small because you're using that to evaluate your model, right? So for example, if your test set only has one sample, right? And you evaluate algorithm on the samples, then you either get it right or wrong, but that doesn't give you much confidence on how well you're actually doing, right? Correct? So in some sense, there's a trade-off between the size of the training validation test set. Right. Ideally, you want an infinite amount of data, right? Then you can have an infinite amount of data in a training validation test set. But yes, but there's no infinite amount of data. So yeah. Okay. Anybody has any other questions? Okay, so this is the typical, what I just discussed with you is the typical training validation test set. And this is, I would say, the dominant scheme in machine learning right now. But in many applied areas, in many areas where people apply machine learning, another popular way of doing things is this k-fold cross-validation. And this typically happens when you don't have enough data, right? So in K-fold cross-validation, you can divide the data into K sets. Maybe you can call them folds, right? So you're gonna repeat, right? For iteration I from 1 to K, you take the ith fold, and let's call this the test fold, right? We're gonna train on the remaining folds, right? And test on the ith test fold, right? And then we're gonna repeat. So basically, so in the first iteration, you would take the first set and you call this the test fold. And then you take the, let's say this is 10-fold cross-validation, right? Where K is equal to 10. So then you take the remaining 9 folds, right? 9 sets, and you train your model on the 9 sets, right? And then you use that train model and you test it on the first fold. Okay, and then you repeat. Now you take the second fold, and the second fold is now your test set. Okay, and you repeat. Okay. So if K is equal to N, this is called leave one out cross-validation. And in general, this is not a good idea. I would encourage, people have shown that this is not a stable scheme, and you should not do it. Yeah. So the problem with the K-fold cross-validation is that it's the same problem as before, right? If one algorithm gives a poor K-fold cross-validation, right? You're not going to tell your boss, oh, sorry, this data does not work. I'm going to give up, right? You're going to try a different algorithm and you're overfit. Okay. So typically what people might do is they will do this thing called inner loop or nested cross-validation, right? So essentially this is called cross-validation. We're going to add another for loop of cross-validation inside, which is why it's called inner loop cross-validation, right? So again, we divide our data into K folds. For I1 to K, we take the ith fold and we call it the test fold, right? And then for the remaining folds, right, we can do another K-fold cross-validation. I use K prime because K and K prime can be different, right? So this can be a 10-fold cross-validation. This can be a 5-fold cross-validation, right? So in this inner cross-validation, you can try different algorithms, different parameters, right? And then you apply the best algorithm to the ith test fold. Okay, and then you repeat, right? So in general, is a bit K-fold cross-validation is more data efficient than the training validation test scheme, but it's less clean, and yeah, it's more complicated, less clean, easy to make mistake. Someone is asking me to repeat the K-fold process again. Okay, so actually maybe the easiest way would be I just quickly draw this, right? So let's say we do a 5-fold cross-validation, right? So let's say we have a, can people see my screen? You can see my screen, right? So let's say we have let's make it easy, make my life easy. Let's say do a 3-fold cross-validation, right? 3-fold cross-validation, right? So then you have your data set, right? You divide it into 3 partitions, correct? Right? So in the first iteration, right, you train using this one. This is used for training. And then you evaluate using the remaining data. So this is your test set. Okay, right? And then you repeat. In the next iteration, right? Then this is now used for training, right? And the remaining 2 sets are used for, sorry, hold on. This, in the second iteration, this is now the test set. So this 2, oh, sorry, I screw up my explanation, my bad. Let's start from the beginning. In the first iteration, this is the test set, this is the training set, right? You use these 2 sets for training, and then you apply to your test set for evaluation, okay? And then you repeat. Now the second fold, right? This is now used for testing, and you use the first fold and the third fold for training, okay? And then you repeat again. The third fold is now the test set, and you use the first 2 sets for training and you evaluate on the third set. Okay, so this is the K-fold cross-validation. Okay. Does that answer your question, Arunava? So so then Emil is asking, why is K4 less clean than training validation test? K4 is actually fine. The problem is when you use the inner loop cross validation, and then you do the inner loop cross validation with different algorithms, right? So as a result, when you do the inner loop cross validation with different algorithms, eventually different algorithms might win for different folds, right? And so ultimately, in the end, you won't have one algorithm that performs the best, right? So that's why it's a bit less. That's why it's a bit less clean. Okay. So Christopher is asking if there are 3 models we want to deploy. Using K4 cross-validation, say model 1 is the best. But this performance is the average of that model trained over different partition of training data. Then do we retrain the model on the entire set to deploy? Yes, correct. So with a K4 cross-validation scheme, let's say you compare 3 algorithms using the K4 cross-validation scheme. One algorithm is the best. Let's say algorithm 2 is the best, right? But actually you have trained this K times, right? So which train model do you use? So what people typically do is that you take algorithm 2 and you train it on the entire data set again, and then you apply it to new data. Does that answer your question, Christopher? And Kayang is asking, yes, okay. Kayang is asking, continue with the inner loop cross-validation. Yeah, the inner loop cross-validation is a bit more annoying to draw. Okay, so I'll just do one iteration, right? So let's say, okay, remember in iteration 1 of the inner loop cross-validation, right? You have this test set, correct? And then you have this training, right? From this 2, right? So what you can do is that you can do, now you have this 2 folds. You can do, let's say, a 2-fold cross-validation, right? Let's say, and you are trying to compare 2 different algorithms. So you can run this on algo 1 and algo 2, right? And then from this 2-fold cross-validation, you find that algorithm 2 is the best, right? And so then you apply algorithm 2 to your test set. Does that answer your question, Kayang? Do you use the train parameters in the second round train? Sorry, I don't understand the question. Chunling. Oh, do you mean that when we apply algorithm 2 to the test set, do I use a train parameter? Is that what you're asking? Yes. So in the 2-fold cross-validation, you find that algorithm 2 is the best. Then you train algorithm 2 on this data set completely, and then you apply to the test set. Yeah. Does that answer your question, Chunling? Cool. Yeah, it's kind of a similar question as Christopher, right? Because when you do a 2-fold cross-validation here, you're only using half of this data to train, right? Correct. And so after you find that algorithm 2 is the best, you can train using both of this data together and then apply to the first set. Okay. And then yes, and then you repeat, and then you repeat, and then you repeat. Now, when you repeat, now this is now the test set, and the other 2 are now the training set. And then you repeat with again, right? So then this is where the why is not clean, because when you repeat it, when this is the test set and this is the 2 training set, you might find that algorithm 1 is better, right? And so things become very messy, right? So when you repeat again, when this is the test set, you might find that in this instance, algorithm 1 is better, right? And so then you might find that in the first time you do it, algorithm 2 is better. For this, algorithm 1 is better, and then for this, algorithm 2 is better. And so things become very messy. This is what I mean by with inner loop cross validation becomes very messy. Emil is asking, oh, hold on. Does it mean algorithm 1 is the original algo, while algorithm 2 is after train 1? No. Gao Yige, no. So when you're doing this inner loop cross validation, right? You are doing a 2-fold cross validation where you're training algorithm 1 and testing it here, and you're doing algorithm 2 and testing it here. So in both cases, these are 2 different algorithms, okay? Or this is typically being used to pick hyperparameters. That's what inner loop cross validation does. Okay. Emil is asking, is validation set invisible to training the model? Yes. So you don't use validation set to train the model. Yes. Correct. Simple example for such a K4 cross validation scheme. I'm actually not sure what you mean. So imagine that you have a, just now I give you the example of the Alzheimer's patients, right? So, ED is asking, right, simple example. So imagine the example I give you about, you're trying to use MRI images to predict Alzheimer's patients versus healthy people, right? So then you can do a 3-fold cross validation, let's say, and you want to use a particular algorithm for classification, let's say support vector machine, right? And so you can do a 3-fold cross validation using the support vector machine, and then you can evaluate your accuracy using that. Emil is asking again, how is it different from the test set if it is invisible? Emil, it's different because you evaluate your performance on the validation set, but if your algorithm sucks, you can repeat again, right? And each time as you develop your algorithm, you can use a validation set, right? So the validation set is used multiple times for evaluation, right? But because you use the validation sets multiple times for evaluation, you might overfit to the validation set. Therefore, it's good to have another test set, to have a test set which is completely untouched that you can use to evaluate your algorithm. Does that answer your question, Emil? Is it possible to do K4 on large data set? Frankly, if you have large data set, I would suggest strongly using the training validation test because it's just a much easier thing to do. Yeah. Yes. Tinda is asking, is K4 cross-validation vulnerable to false data? What does that mean?
Professor, so if for the 3-fold cross validation, so if 1 fold is very, very wrong, so I think it will screw up the entire training. So if you only have like,
I see. Actually, this problem would be worse in a training validation test scheme, right? So in the training validation test scheme, if you're unlucky, your test set or training set is bad, you can be screwed, right? Whereas in the 3-fold cross validation, because you're doing a round robin, right? So actually you're kind of protected against that. So actually in some applications, people recommend that, let's say you do 5-fold cross validation, but you repeat it many times so that you don't get very lucky or unlucky when you split your data into the 3 sets, right? So actually, if you're worried about stability and that you're not too lucky when you divide it into like training validation test set, then actually K4 cross validation be better.
Okay, thank you.
Yeah. Is K4 cross validation more suitable for classification or regression? It doesn't matter. It can be for classification or regression. And inner loop cross validation is a lot more resource intensive. I agree, especially for deep learning algorithms where you have to tune a lot of hyperparameters. It is actually a huge pain. So for deep learning, most if you can use training validation tests, you should definitely use that. So because in the 10-fold cross validation, you need to tune your hyperparameters 10 times, right? Correct? Yeah. So it's a huge pain. Yeah. Okay. Shall we continue? Yeah. Okay. So another important consideration, besides all the stuff I've talked, right? Another important consideration is that actually computation complexity is important. So basically, there was a Netflix contest back in like 2006 or something, and the winner is like will win $1 million, and basically they want to be able to predict movies that people enjoy watching, right? And so I mean, there was a winner who won $1 million, a team who won $1 million, but actually they ended up not using the algorithm because it was too complicated, right? And so actually sometimes the best algorithm is not the one that performed the best. You also need to take into account whether you know, it's easy to maintain and so on. So simplicity sometimes is important. Okay. Another important point is that back in the old days, because Netflix was mailing people DVDs, right? And so it was very important that people were able to like the DVDs they pick, right? Because there's time taken for Netflix for you to receive the DVD, And if you don't like the movie, you need to mail the DVD back to Netflix, right? And so if you end up not liking the DVDs you get, then you will really not want to have what you will really not want to go with Netflix, right? But nowadays, because Netflix is actually streaming, so actually this is actually less of an important issue. So the lesson here is that sometimes you don't need a machine learning algorithm, right? So in this case, basically because of streaming, is actually, this becomes not so important, not so critical to their business. Okay. The other thing we should mention is that all models are wrong, but some are useful, right? And in fact, there's a theorem from Daniel Warpert showing that there is no best model that works for all problems. So that's a result. We have to develop different models, different algorithms to cover different kinds of data. Okay, so this is why there's so many different machine learning algorithms out there, right? And that's why we all have a job for now. Okay, yeah. Okay, so so in this class, we're going to assume that we're only going to focus on these two steps, basically choosing a model and training a classifier. Okay, and in the first part of this course, there will also be a strong bias towards our probabilistic approaches. Okay, so one thing is that in at ECE we have a deep learning course, and this is the non-deep learning course. The reason is that we want to also teach non-deep learning machine learning, right? So in certain applications, actually deep learning does not beat classical machine learning. So this is a paper from Google themselves, right? And you can see that if you look at their appendix, and if you look at the confidence interval, the deep learning model is no difference from basically this logistic regression. Okay, so in many applications, actually, deep learning might not work better than simple models, classical models. Okay, so and then machine learning is cyclical, right? So we're hoping not to teach you just the popular stuff, but basically knowledge that will be helpful for you in the future as well. Neural networks were hot in the 80s, and then they become unpopular for 30 years, and then now they're super hot again. Okay, so we want to teach you not just what's popular. Okay, so just an interim summary. We have talked about different kind of machine learning algorithms: supervised, unsupervised, semi-supervised reinforcement learning. We talk about how deploying a machine learning system is an iterative process, right? We have to collect data, we have to choose features, we have to choose model, we have to train, test, and then if it doesn't work, we have to repeat. Okay. Feature engineering is important. A lot of time, if we choose the right features, then even a simple model works well. So nowadays with deep learning, you can, in principle, learn the features, right? But with the deep neural networks, there are other things you have to tune, of course. So instead of doing feature engineering, you have to do other stuff. So in decision theory, not all errors are equal, are the same, right? Depending on what kind of errors are important, we might need to modify our algorithm accordingly. Okay. We talk about the curse of dimensionality, right? In general, roughly speaking, increasing the number of features and the model parameters will improve the training error. The test error might also improve, but eventually it will become worse, right? And this is called overfitting. We typically, to evaluate our data and to make sure we don't overfit, we typically employ a training validation test scheme. We train our model on the training set and evaluate on the validation set, right? And when we're happy with our results, we then evaluate on the test set. And so basically, you should only use the test set at the very end, right? So instead of training and test set, we can also use a K4 cross-validation scheme. Okay, and computational complexity is also very important, right? We want an algorithm that, it's not just about performance, but we might want an algorithm that's simpler or take less time, easier to maintain, and so on. Okay, and then basically there's not a universal algorithm that works well for all problems. And in this class, we'll consider different models. Okay. Okay, so here are some optional reading. This what I've shown you so far is from Doodle and Hart chapter 1, and the Kevin Murphy textbook provides different introduction, but there's some typos in there. Okay, Does anyone have any questions? If not, we can take a break. We are actually, what's the difference between deep learning and classical machine learning? So in deep learning, typically it's based on like neural networks. Most of the algorithms you learn in this class will not be deep learning. Yeah. Yeah, a deep learning typically has, as Arunava says, they have multiple layers of neurons, fake neurons. Yeah. Anyway, okay. So, is the curse of dimensionality a problem due to inability to visualize it? No, the curse of dimensionality is a problem because when you have too many features or if your model is too complex, then you might overfit to the data and you perform poorly. Yeah. So it has nothing to do with visualization. So for example, in here, right? So here, you know, we have this model is very complex. We can visualize this model, right? As you can see here, we can visualize it, right? But actually we're not performing so well because the model is too complex. Okay, yeah. Cool. Let's take a 3-minute break. Let's come back at 7:05. Okay, so less than 4 minutes. Okay, and then we will continue. Okay, it's 7:05. I'll appreciate if y'all can turn on your video again. Okay, let's start again. Let's see how do I do this. Okay, hold on, let me think. Let me bring up the chat again so I can see your questions. So someone is asking me whether they can get e-copies of the book. You can certainly do it, but I cannot get it for you. If you know what I mean. Yeah, there are ways for you to get e-copies. You can pay for it, or you might even be able to get it for free, but I cannot get it for you. Yeah. Okay. All right. Any other questions? So by right, I mean, these are just optional texts. In theory, if you just read, if you just come to the lecture, if you read the detailed notes at the bottom of the lecture notes, if you miss something in class, and if you do the exercise, and I also give you the solutions, right, for the exercises, in theory, you don't need a textbook. Yeah. Hope that helps. But some students do find the textbook might be, helpful. It might explain some stuff in more details. Okay. Okay, so now for this second part, I'm going to review probability, right? So most of these concepts should not be new to you because, as I said, that's the prerequisite for the course, right? And if you find that most of these concepts are new to you, then you have trouble for this class, unfortunately. Okay. Okay. So basically, roughly speaking, a random variable x is a quantity that's uncertain, right? It may be the result of a random experiment, like flipping a coin. It may be the result of a real-world measurement, like let's say if you measure the temperature in the room, or it can be the result of a COVID test, right? As we all have done, right? So if we observe x multiple times, right, we get different values. Some values are going to occur more often than others, so this is captured by the probability distribution P of x, right? So if x is discrete, then P is the probability mass function, or PMF. Oh, sorry, PMF. Yeah. If x is continuous, then P is called a probability distribution function, or PDF. Okay. Now, a discrete random variable takes on a discrete set of values, right? So, for example, let's say we have a dice. This is a biased dice. So 5 is the most likely value, 3 is the least likely value, right? And by discrete, we don't mean that it can only take on integer values. It means that there is a finite or countably infinite values, right? So in this case, the dice is now like 1.5, 2.3, and so on. Okay, right? The least likely value is now 3.3. Okay, so in this case, if you sum the PMF, right, the sum is equal to 1. Okay. So on the other hand, a continuous variable is one that takes on a continuum or uncountably infinite number of values, right? So for example, here's the time taken to complete a test. Okay. So there are many discrete random variables, Bernoulli, categorical, and so on, right? Wikipedia has information about each type of random variables. And you should have seen these distributions in your undergraduate probability course, except maybe categorical distribution. Okay. Actually, you have seen it. It's just that they don't call it categorical distribution. Okay, let's continue. So let's talk about the Bernoulli distribution first, right? So the Bernoulli distribution is basically a experiment where there can only be two outcomes: x equal to 0, x equal to 1, right? Typically, x equal to 0 might mean failure, 1 is success, or 0 might be tail, and 1 might be head of a coin toss. Okay. There's a single parameter lambda. Lambda is a number between 0 and 1. The probability that x is equal to 0 is 1 minus lambda. The probability x equals 1 is lambda. Okay. You can write it in a fancy form, right? P of x is equal to lambda to the power of x times 1 minus lambda to the power of 1 minus x, right? The reason why people like to write it in this form is sometimes it's useful to write in this form is that this is like an if statement, right? This is saying if x is equal to 0, we use this formula. If x is equal to 1, we use this formula, right? Sometimes it's useful to write a single formula for the probability distribution, which is this, right? So when x is equal to 0, you plug in x equal to 0. X equal to 0, lambda to the power of 0 is 1, right? So 1 minus lambda to the power of 1 minus 0 is 1 minus lambda, right? And so when p of x is 0, then this is 1 minus lambda. This formula here is 1 minus lambda, right? On the other hand, when x is equal to 1, what will happen? When x is equal to 1, 1 minus lambda, 1 minus 1 is 0, right? So 1 minus lambda to the power 1 minus x is 1. So lambda to the power of 1 is lambda, right? Correct? And so essentially this compact formula is equivalent to this. Okay. And then in short, we can write P of x as the Bernoulli distribution of x given the parameter lambda. Okay. Any questions? Okay. So a categorical distribution is like the Bernoulli distribution, except instead of 2 outcome, in the Bernoulli distribution, you have 0 or 1, right? In a categorical distribution, you have k outcome. So the categorical distribution is controlled by lambda 1, lambda 2 to lambda k. The lambdas are between 0 and 1, and they have to sum up to 1. Right? So if you sum up all the lambdas, it's equal to 1. Okay. So basically, the probability that you get the kth outcome is equal to lambda k. Okay. So the probability that x is equal to k is lambda k. Right. Again, we can write this in a very compact form. Right. So let's say x is equal to k. We can represent it as a basically it's called one hot vector, but basically let's say you have let's say capital K is 5, right? So capital K is 5. So there are 5 possible outcomes. So you can represent it as a vector of length 5. All the entries are 0 except for k, right? So let's say the probability that x is equal to 4. Sorry, let's say we're talking about x equal to 4. We can represent this as 0, 0, 0, 1, 0, right? So so if we're talking about x is equal to 2, then it will be 0, 1, 0, 0, 0. Okay. And so like before, like the Bernoulli distribution, we can write this in kind of a compact format, right? Probability that x is equal to k, right, is product from j equal 1 to capital K, lambda j to the power of ekj. And that's equal to lambda k, right? You can work it out yourself, but basically, okay, let's work it out, right? So let's say small k is 4, so E4, right? So 0, 0, 0, 1, 0, right? So E4j, right? If j is 1, right? If E4 1 is this entry, which is 0, right? So lambda 1 to the power of 0 is 1, right? How about lambda 2? Lambda 2 to the power of ek2. ek2 is also 0, correct? So lambda 2 to the power of 0 is also 1, right? So the only entries that survive is actually when j is equal to 4. Then we have lambda 4 to the power of ek4, right? And what's ek4? ek4 is equal to 1, right? And so we have lambda 4 to the power of 1, which is lambda 4. Okay, so we end up with lambda 4. Okay. Is everyone okay with this? Any questions? Cool. Thanks, Emil, for responding. Okay, good. Oh, sorry. And so yeah, so this is we short form it as categorical distribution of x given lambda. Okay, and there are many continuous random variables as well. Gaussian, uniform, exponential, beta. I won't really go through. Okay. Well, like just to remind you, Gaussian. For the Gaussian distribution, right, looks like this. This is the PDF of the Gaussian distribution. P of x is 1 over square root 2 pi sigma square. E to the power of minus x minus mu square divided by 2 sigma square, right? So the mu is the mean of the Gaussian distribution, and the sigma square is the variance. So sigma square has to be greater than 0. Okay, and this is an example plot of the Gaussian distribution. As we go from left to right, the mean goes from minus 3.4 to 0 to 1.5. So the curve is shifted to the right. the variance goes from 0.25 to 1 to 4.41. So you can see that the curve becomes fatter because the variance is increasing. Okay. But the area under the curve is equal to 1. And so as the curve becomes fatter, the curve has to go down. Okay. So that's why the curve becomes shorter. Okay. Right. Anyway, I think actually I already covered what I want to say in this slide. Okay. Any questions about Gaussian? That should be pretty, you should have seen all of this as well. Okay. So what about when we have two random variables, right? So imagine we have two random variables, X and Y. So some combinations are more likely than others, right? So this is captured by the joint probability distribution, right? So we can write P of X and Y as the joint probability distribution of X and Y. Okay. Now, here's an example of where X and Y are discrete random variables, right? So the white square, the size represents what is the how big the PMF is, right? So a bigger white square means that you're more likely to observe this pair of X and Y, whereas this pair of X and Y is unlikely or maybe impossible. Okay. So if we take the joint distribution P of X and Y, if we sum over X and Y, is as B equal to 1. Okay. And here's X and Y. Now X and Y are continuous random variables, right? So the brightness represent the value of the PDF, the joint probability distribution function. So this is a very highly likely pair of values, right? And this is an unlikely, this is a somewhat likely, and this is a very unlikely pair, right? Now, if we take the joint distribution of X and Y, and we integrate over all values of X and Y, we get 1, right? So in other words, if we integrate over these yellow, red, and blue values, right, and black values, we get 1. Okay. And now here's a mixed distribution. So here X is continuous and Y is discrete. Y can take on 5 possible values, right? And in this case, if we take the joint distribution P of X and Y, if you integrate over X and you sum over Y, you get 1. You have a question, Christopher? Oh, oops. Distraction. Anybody else have a questions? A real question. Okay, good. Oh, okay. Can you explain the third case? So in the third case, there are again 2 random variables. So in this case, both are discrete. In this case, both are continuous. In this case, X is continuous, right? And Y is discrete. Sorry. So in this case, P of X and Y is, you don't call it a PMF, you don't call it a PDF. It's just a mix of 2 variables, right? And so X is, in this case, this is the joint distribution P of X and Y. If we integrate over X and we sum over Y is equal to 1. Cool. All right. Questions? If not, I'm going to talk about the law of probability. So now I'm going to talk about some facts about this probability, right? So basically, if we have a joint distribution P of X and Y, how can we recover the marginal distribution P of X or P of Y, right? So this is the visualization here. Sorry, let me tell you the formula first, right? So if we have P of X and Y and both are discrete, if we sum over Y, we get P of X. If we sum over X, we get P of Y, right? So this is a visualization. What is one example of the third case? It's actually quite easy. You actually see this kind of mix. You can easily get these mixed cases quite easily, right? Because random variables are anywhere. So for example, X might be your body temperature and Y might be whether you have COVID or not. So whether you have COVID or not is a binary random variable, right? So you either have it or you don't. And X is your body temperature, which is presumably continuous. Does that answer your question? Yeah. If Y is discrete, if X is discrete, Y is continuous. Yeah, if X is discrete, Y is continuous, then you need to do the opposite. You need to sum over X and you integrate over Y. Basically, in general, if it's continuous, you want to integrate. If it's discrete, you want to sum. Does that answer your question? Yep. Okay. Okay, so coming back here, right? So to get P of X, So this is a representation of the PMF, the joint probability mass function of x and y, right? To get P of x, we sum each column, right? To get this white box. To get P of y, we sum this row, right? To get this white box. Okay. We can repeat with when x and y are continuous random variable, right? So in this case, if we have P of x and y, because they're continuous random variable, we integrate y, we get P of x. We integrate x, we get P of y. Right? And again, this is the representation of the PDF, the joint PDF of x and y. So x-axis is x, y-axis is y. Okay. So if we integrate vertically, so we're integrating y, right? Then we get P of x. If we integrate horizontally, so we're integrating x, right? We get P of y. Oh, I don't have a picture of a mixed distribution, but okay, yeah, it's fine. Yeah, okay. Let me give you any questions so far? Any other questions? I think y'all so far are not shy in stopping me, so that's good. So, oh yeah, sorry. So this integration process, there's just a name for it. It's called marginalization. I don't know where the name comes from, but it's called marginalization. Yeah, we call this, yeah, this is called marginalization or law of total probability. It's just a name. Yeah, I don't have a good reason why it's called marginalization. Yeah. Okay, so here's an example. Let's say this is a joint distribution of x and y. X can be 0 or 2.5, y can be -3, -1, and 2. So this is a joint distribution. So the first thing to check is that you can sum up all these values, it sums to 1, right? That I didn't make a mistake, right? Okay. So let me ask you, what is P of y and what is P of x, right? So P of y would be to obtain, oh, I guess I did P of x first. To get P of x, you need to sum each column, right? So 1/8 plus 1/8 is 1/4. And half plus 1/4 is 3/4. So P of x is 1/4 and 3/4. Sorry, P of x is equal to 1/4 when x is 0. P of x is equal to 3/4 when x is 2.5. Okay. We can repeat the same thing with P of y here, right? So to compute P of y, remember now we have to sum over x, right? So to compute P of y equal -3, we need to sum over x. So 0 plus half is half. To get P of y equal -1, 1/8 plus 1/4 is 3/8. To get P of y equal to 2, you have 1/8 plus 0 is 1/8. Okay. And so as a very good sanity check, you can check that half plus 3/8 plus 1/8 is 1. Similarly, 1/4 plus 3/4 is 1. Okay. Does anyone have any questions? Okay, so as I said, hopefully by right, this should be revision. Okay. There will be some non-revision stuff later, but it will be, yeah, at the end. But yeah, so far it should be revision. Okay. Oh, Nitin is asking, what are the values -3? So these are the possible values of y. So y can take on value -3, -1, or 2. X can take on value 0, 2.5. Does that answer your question? Yeah, sorry, I was unclear, I guess. Yeah. Thanks for asking. Okay. So so conditional probability, right? Suppose we have two random variables x and y, right? So suppose y is equal to y1, then P of x given y equal y1 is how likely x will take on various values given this observation, right? So for example, oh, why did my thing sound open? Sorry. For example, if y is your COVID test, right? Y is the result of your COVID test, and x is whether you have COVID or not, right? So if your COVID test is positive, what's the probability you have COVID, right? Correct. So this is actually obviously a very useful thing to know, right? So we read this as conditional probability of x given y is equal to y1. Okay, so we can illustrate this here. So here's the plot, right? So again, this is a visualization of the PDF of x and y. X-axis is x, y-axis is y. Bright spot means it's more likely, right? So to compute P of x given y equal y1 is basically a slice of this distribution, right? Except that a slice of this distribution doesn't integrate to 1, right? So we need this extra condition, which is that P of X given Y equal Y1 is a distribution over X, right? So if you integrate over X, it has to be equal to 1. Similarly, when Y is equal to Y2, if you cut one slice through here, you get this distribution here, right? So, so this is a distribution over X. So if you integrate with respect to X, it has to be equal to 1, right? And so the actual formula is that you take a slice of the joint distribution and then you need to normalize it so that it's equal to 1, right? So this is so if you take a slice of joint distribution, it's P of X and Y equal Y star divided by P of Y equal Y star, okay? And so this is actually P of X given Y equal Y star is equal to this, okay? So this formula, this denominator is necessary in order to ensure that the conditional probability integrates to 1. Is everyone okay with this? Or do I need to show this? Anybody? Or this is fine, right? So if you try integrating this, you'll find that this is equal to 1. Okay. So if you integrate this with respect to X, you'll find that this is equal to 1. Okay. And so we can obtain the denominator, right, by doing a marginalization of the joint distribution, P of X and Y equal Y star, because if you integrate with respect to X, right, then this becomes P of Y equal Y star. This is the law of total probability or marginalization. Okay. Does anyone have any questions so far? If Y is continuous, then is P of Y equal Y star equals 0? No. Well, it depends on what is P. So in this case, P is the PDF here. So it's not the actual probability. Yeah, Yinzhen. So indeed, the probability of Y is equal to 0, right? But in this module, well, in my first half of the module, when I write P, I tend to mean either PDF or PMF. So if it's a continuous variable, you can assume it's PDF. If it's a discrete variable, you can assume it's PNF, right? The reason why I'm making it vague is that let's say you have this mixed distribution like here. Sorry, hold on. In this mixed distribution, right? When y-axis is continuous, y is discrete, we don't really have a name for this. We don't. At least I don't know whether to call it PDF or PMF, right? So in this part of the module, we simply call it P. Does that answer your question, Yinchuan? Yeah. Okay. Very good question. I assume that this might not be clear for many people as well, right? So for the purpose of this course, if you see P, well, for my half of the course, if you see P, it means PMF or discrete random variable. If it's continuous random variable, P is PDF. Okay. Oh, sorry. Yeah. Okay. So let's continue, right? So we can write this in a more compact form, which you might have seen before. P of X given Y. I just dropped the Y star. So it becomes P of X given Y. So this one I dropped the Y star. So this becomes P of X and Y. Then this one I dropped the Y star. This becomes P of Y, right? So P of X given Y is equal to P of X and Y divided by P of Y. Okay. And then we can rearrange it and to get this, right? So we can rearrange it. So in this case, let's say if I bring P of Y over to the other side, so then P of X and Y is equal to P of Y times P of X given Y, right? And it's a symmetry here. So this is also equal to P of X times P of Y given X, okay? Which I'm sure many of you have seen this formula. Is everyone okay so far? Any questions? Okay, let's do a quick exercise then, right? So this is the same joint distribution as before. Again, X can take on value 0 or 2.5. Y can take on value -3, -1, and 2. This is their joint PMF, probability mass function. This is P of X, this is P of Y. Right now, I want to ask you, what is the P of X given Y equal -1? Okay, So how do we compute this, right? So we can use the formula P of x given y equal -1 is equal to P of x and y equal -1 divided by P of y equal -1. Okay, right? And then at this point, you realize that x can take on two values, 0 or 2.5, right? So we actually have to do two calculations, right? So we have to do P of x equal to 0 given y equal -1 and P of x equal to 2.5 given y equal -1, right? And so we can do this. Let's plug in the formula. This is equal to, the top one is equal to P of x equal to 0 and y equal -1 divided by P of y equal -1. Okay. And so we can grab the value x equal to 0, y equal -1 is this one. So 1/8, which we can copy here. And P of y equal -1 is 3/8, which we can copy here. And so this is 1/3. Okay. And we can repeat with the denominator. Right now, the numerator is P of x equal 2.5 and y equal -1, which is 1/4. So I put here. P of y equal -1 is 3/8, which I put here. So it's 2/3. Okay. And again, as a sanity check, 1/3 plus 2/3 is 1. Okay. And Mio, I just noticed that you type in nope. Is that a question or that's a comment? Yes. Okay. Okay. I guess it's fine. Oh, okay. Okay. I see. Yeah. Okay. Good. I like people. Yeah. Thanks for, joining in. It's fun. Okay. All right. Okay. So does anyone have any questions before I continue? Okay. Fine. Let's continue. Okay. So base root. Okay, again, I think most of, well, I hope all of you should have seen this before, right? This should be a prerequisite for the class. Okay. So just now I've shown that P of x and y is P of y times P of x given y. And I've also shown that P of x and y is equal to P of x times P of y given x, right? What if we equate this two equation and then we get this, right? So then if I move this here to the left side and I move this equation here to the right side, okay? And then the next thing I'm going to do is I am going to move P of x to the left hand side. And so we get this, right? So P of y given x is here. P of y times P of x given y is the numerator. And P of x, I move to the denominator. And so we get this denominator here. Okay, so far so good. Okay. So, I mean, this is basically called the base root, right? And I'm going to give you a few more versions of this, right? So P of x can be written as integration P of x and y dy. So I wish I can put here. This is the law of total probability or marginalization. So here, when I write this, this means that I'm assuming y is continuous. Okay. And P of x and y is equal to P of y times P of x given y. And so we can put this here. Okay. And so these three formulas are called base root, right? And in all of this, y is a continuous random variable. If y is discrete, then all we need to do is to replace the integral with the sum, right? So I changed the integral to the sum. Okay. Okay. So this is base root, and there's a few names for this, right? So P of y given x, this is called the posterior. The posterior is posterior means behind, right? Or the back, right? So this is the probability of y after we observe x. Okay. So P of y is called the prior. It's the probability of y before observing x. Okay. And P of x given y is called the likelihood. It's basically the propensity for observing certain value of x given a certain value of y. Right. And P of x is called the evidence term. For now, probably there's no good reason why it's called the evidence term. But yeah, anyway, just know that the denominator is called the evidence term. Okay. Does anyone have any questions? If not, let's do an example on the base root. Okay. Now base root. Okay. So suppose there's a 40-year-old woman doing a mammogram. Let x equal to 1 if mammogram is positive and y equal 1 if the woman has breast cancer, right? So suppose the test is positive. What is the probability the woman has breast cancer, right? So based on this question, you should be able to write down probability of y equal 1 given x equal to 1, right? Probability the woman has cancer given the vertical line is given that the mammogram is positive. Okay, so to compute this probability, we need to know a few things, right? So suppose the sensitivity of the test is 0.8. Now that COVID is now very common, I'm sure you guys know all this, all this terminology now. We're talking about COVID test, for example, right? So sensitivity is the probability that the test is positive, given that the woman has breast cancer is 80%. I'm just making it up, okay? And false positive rate is the probability that the probability that the test is positive, given that the test is, probability that the test is positive given that the woman does not have breast cancer, right? That is 0.1. Okay, as you can see that this is worse than the COVID test that we have. So the prior here is the probability of breast cancer, right? So for example, the probability of a 40-year-old woman having breast cancer is 0.004, right? So this means that 0.4% of 40-year-old women have cancer. Okay. Now with this, we can apply to Bayes' rule, right? So we want to compute P of y equal 1 given x equal to 1. This is the probability the woman has cancer given the test is positive, right? So this is equal to, this formula is just the Bayes' rule, right? P of y equal 1 times P of x equal 1 given y equal 1 divided by, so this is the prior probability the woman has cancer. This is the likelihood, the probability the test is positive, given that the woman has cancer, right? Divided by the denominator. So this is the prior probability of the woman having cancer times the probability that the test is positive, given that a woman has cancer, plus the probability that the woman does not have cancer, times the probability that the test is positive, given that the woman does not have cancer. Right. So the denominator here is actually the probability that the woman, the probability that the test is positive. Okay. So now we can plug in the numbers from above, right? So prior probability P of y equal 1 is 0.004, so we can plug it in. Probability the test is positive given the woman has cancer, that's 0.8, so we can plug it in. Again, this is 0.004 because prior probability of cancer times 0.8 plus prior probability no cancer. So this is 1 minus 0.004, which is 0.996. And then this is probability that x equal to 1 given y equal to 0, which is 0.1 according to here. Okay, so we get 0.031. So this means that even though the test is positive, actually the probability of the woman having cancer is very low, 0.03. Okay, so this is why the US government no longer recommend routine mammograms for women in their 40s, basically because, there's low chance of the woman having cancer even when the mammogram is positive. Okay. Does anyone have any questions about this? Okay. So everyone is an expert in Bayes' rule now, right? So actually, I received this message from the government this morning, right? It says that there are 43. I guess some of you are not in Singapore, but anyway, in Singapore, not currently in Singapore. In Singapore, you can sign up for these messages. So there are 43 infected patients with COVID-19 who are seriously ill. Okay, I guess let me highlight what is important. That's fine. So let's see, there are 43, right? Of these, 36 are unvaccinated or partially vaccinated, so 36, and 7 are vaccinated. Okay, so I can see why the government is doing this, but can someone tell me why this is the wrong numbers to report? Anybody? Yes, exactly. So the issue is that the government is, from these numbers, we can compute probability probability vaccinated given seriously ill, right? And probability unvaccinated given seriously ill, right? So this is actually the likelihood, right? So, but actually, I guess the government is trying to convince people to take the vaccine. So what we actually need is probability of seriously ill. What we really want is vaccinated, and probability seriously ill given unvaccinated, right? Correct. To be fair, actually, this is being very conservative, right? So because there are many more people who are vaccinated now than unvaccinated, so actually, in some sense, the government is not cheating us, right? If anything, this is they could have presented even better numbers than this. Yeah. The problem would be if, let's say, at the end, at some point, let's say 99% of the population is vaccinated, then suddenly we might find that many of the people who are seriously ill are actually vaccinated, right? And then if you use the same statistics, it would imply that it would seem as if that, the vaccination is no use. And indeed, actually, this has been an issue in overseas news report, where I think there was some case in the US where they report that 75% of the people with COVID were vaccinated, right? And so immediately people, this vaccine skeptic on Twitter immediately are like, oh yeah, it's because, vaccine doesn't work and so on, right? But in some sense, we're using the same logic here, and it is wrong. Yeah. In the cancer case, why the sensitivity and prior adds to 1? Oh, does it add to 1? Sensitivity. Hey, what do you mean by adds to 1? 0.8 and 0.004 does not add to 1, right? How are you? What's your question? Oh, you're saying why doesn't it add to 1? Because they're a completely different thing, right? So the prior here is the prior, like without doing the test, what is the probability of the woman getting cancer, right? Correct? Whereas the sensitivity is a function of the test, right? If your test is good, this sensitivity will be high, right? This sensitivity can be 0.9, 0.95, and so on, right? Does that make sense? So these two numbers do not need to add to 1. Does that answer your question, Harry? They are not like these two numbers are not a probability distribution, so they don't need to add to 1. Yeah. Okay. Okay, cool. Anyway, so any questions before I continue? Let me see. We are 136 slides in, still like 70. I can continue a bit longer before we take a break, if y'all don't mind. We can do a bit more. Okay. All right. Okay. So independence. The next concept is independence, right? So I want to point out a special situation, right? So knowing X tells us nothing about Y, and knowing Y tells us nothing about X, right? So in this situation, we say that X and Y are independent, right? So if X and Y are independent, then the conditional probability of X given Y is the same as P of X, right? And the P of Y given X is equal to P of Y, right? Because Y tells us nothing about X. So even after we observe Y, right, because it tells nothing about X, we still get X, right? Similarly, after we observe X, because X tells nothing about Y, so this is equal to P of Y, okay? Now, if X and Y are independent, then the joint distribution factorizes into the product of the marginal distribution. So this is kind of very wordy. Let's see mathematically what's going on, right? So P of X and Y is equal to P of X times P of Y given X, right? And because they're independent, so P of Y given X is equal to P of Y, okay? So conversely, if joint distribution can be factorized into product of marginal distribution, then X and Y are independent. This is not so obvious, but I forgot whether that's one of the questions in the assignment. Yeah, I think it's one of the ungraded assignment question where they show this. Yeah. Okay. Does anyone have any questions? Okay, so let's talk about expectation of one random variable, right? So expectation tell us the average value of some function f of x, taking into account the distribution of x. Okay. So the expectation of f of x is equal to sum over x times f of x p of x, right? If here this is assuming x is discrete, if x is continuous, then we need to integrate with respect to x. Okay. Oh, sorry. Okay. So there are a few very special cases, right? So this is the formula for the expectation of x. Sorry, expectation of f of x, right? If f of x is equal to x, then expectation of f of x is equal to expectation of x, and we call this the mean of x. We can think of this as if we observe x many times, and then we average x, then we get a mean of x. Okay. And there's another special case is when f of x is equal to x minus the mean of x squared, right? So in this case, expectation of x minus mean of x squared is equal to sigma x squared. So sigma x squared is called a variance, right? And sigma x is called a standard deviation, right? So variance is basically a measure of how likely x is going to be far away from the mean, right? So essentially you can think of it as we observe x many times, and every time we compute the square difference between x and the mean of x, right? And then we average the square difference many times, and so we get variance of x. Okay. Does anyone have any questions so far? Cool. So let's consider our previous example again, right? And we're going to compute the mean of x. Right? So this is the previous example, same as before. Now we're going to compute the mean of x, sum over x, p of x. Okay. So we're going to use the formula. So x takes on how many values? X can be 0 or 2.5, right? Which means that there's two terms in the sum. So we have 0, x is equal to 0 times 1/4. P of x with 0 is 1/4, plus x is equal to 2.5 times p of x equal to 2.5 is 3/4, so it's 3/4. So if we do this, it becomes 1.875. Okay. We can repeat this again, and then we get minus 1.625 for mean of y. Okay. I won't work it out unless someone wants me to. Does anyone have any questions or want me to work it out the mean of y? Everything okay? Okay. Now, how about the variance of x, right? So the variance of x, right? So the variance of x is defined the expectation of x minus the mean of x squared, right? In terms of the formula, you write this as sum over x, bracket, x minus mean x squared times p of x, right? Okay. Again, x can take on how many values? 0 or 2.5, right? So there are two terms to this sum. So the first term is 0. When x is equal to 0, you have 0 minus the mean of x, which is 1.875. So minus 1.875 square. The square is from here. P of x is 1/4. So we put 1/4 here. The second term is x is 2.5. So x is 2.5. The mean is always the same. It's always 1.875 from here, right? And then 3/4 is the probability that x equal to 2.5, which is 3/4. Okay. And so if you do that, we get 1.171, 1.172. Yeah. Okay. Any more questions? Cool. Right. Okay. So then we can talk about expectations of two random variables. Okay. So here expectations of two random variables, it tells us the average or the expected value of some function f of x of y, right? Taking into account p of x and y, right? So you can see that the formula is very similar to before, right? So we are interested in the long-term average of f of x and y, taking into account how likely x and y are supposed to appear. Okay, so we have f of x and y times p of x and y dx dy. Okay. So there is a special case here, which we should all know is called covariance. This is when f of x and y is x minus mean of x times y minus mean of y, right? So there's a special notation for it. People use COV, x and y, which is the covariance of x and y. So covariance of x and y measures how much two variables change together, right? So if the covariance of x and y is positive, right, this means that every time x, sorry, not every time. So whenever x is greater than the mean of x, then on average, y is greater than the mean of y, right? So if x is big, y is likely to be big. If x is small, y is likely to be small, okay? The covariance of x and y is negative. This means that whenever x is greater than the mean of y, then on average, y is less than the mean of y, right? So when it's negative, this means that when x is big, y tends to be small. When x is small, y tends to be big, okay? Any questions so far? Can we say the covariance function has two independent random variables? No. So the covariance function takes in two random variables, x and y. If x and y are independent, then the covariance is 0. So we should remove the word covariance, independent. Yeah, right. Yes, so covariance and correlated are very similar. Yeah, it's just difference of MU is asking that they're correlated. Yeah, so the difference is a normalization factor. Okay. So let's do an exercise, right? So here, let's consider the previous example again, right? So the mean is 1.875, mean of x is 1.875, mean of y is minus 1.625, right? So we want to compute the covariance of x and y. There's this formula, right? This is the formula sum over x, sum over y. F of x and y is now x minus mean of x times y minus mean of y, p of x and y, okay? So there are 6 pairs of x and y, right? Because x has 2 possible values, y has 3 possible values, right? So together that's 6 pairs. So there's 6 terms in the sum, right? So the first term is when x is 0 and y equal minus 3, right? So x is 0, y equal minus 3. The mean of x is 1.875, so minus 1.875. The mean of y is minus 1.625, so is plus 1.625 times the probability of x and y, in this case is 0, so we put 0 here. Okay, is everyone okay with this? I'm going to repeat just one more time. So one more time. So in this case, x is equal to 2.5 and y equal minus 3, right? So x is equal to 2.5, y is equal to minus 3. Okay. Mu x is always 1.875, so this is minus 1.875. Mu y is minus 1.625. So is plus 1.625. And then P of x and y is half. So we imply half here. Okay. Okay, so if we continue, if we repeat, blah, 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 we get minus 1.328125. Okay. So the covariance is negative. It kind of makes sense because when x is small, let's say when x is 0, right? Then y tends to be big, right? Correct? When x is big, y tends to be small. Y tends to be minus 3 or minus 1, right? When x is small, y tends to be minus 1 or 2. Okay, so this is why is the covariance negative. Nitin is asking me, are covariance and correlation the same? They are not the same. Correlation is covariance divided by, if I remember correctly, the standard deviation of x and standard deviation of y. Yeah. So they're similar but not the same. Yeah. Okay. Any questions so far? Okay. So rules of expectation. Let's see. So the expectation of a non-random constant is itself C, right? So if A and B are non-random constant, then expectation of A times F plus B times G is equal to A times expectation of F plus B times expectation of G. So this is a linearity of expectation. Okay. So the covariance of X and Y is equal to expectation of xy minus expectation of x times expectation of y. So one consequence is that the variance of x, right, is actually the same as the covariance of x with itself, right? So the covariance of x with itself, if you plug it in, so becomes expectation of x squared minus expectation of x times expectation of x, right? So expectation of x times expectation of x is expectation of x squared, okay? Now, if x and y are independent, then expectation of f of x times g of y is equal to expectation of f of x times expectation of g of y. So in other words, right, if x and y are independent, then the covariance of x and y is 0, right? And the reason is that expectation of x and y, expectation of x times y is equal to expectation of x minus expectation of x times y is equal to expectation of x times expectation of y. It will cancel out this term, so it's 0. Okay. So when x and y are independent, the covariance is 0, but the converse is not true. Covariance of 0 does not imply independence. Okay. Does anyone have any questions so far? Okay, so let's see. I think let me think. After this one we can take a break. You guys must be getting tired. Well, I'm getting tired too. Okay, so yeah. Okay, the last part before we talk about n random. Now we are still in the section called 2 random variables, correct? So in 2 random variables, oh sorry. Why is covariance equals 0 not imply independence? Actually in the ungraded homework assignment, you will actually be asked to do an exercise showing that. Yeah. So you can do the assignment and try for yourself first. Okay. Yep. Do I? Is there? I think there's an assignment. If not, yeah, I can't remember. I think it should be there. Yeah. Okay. Yeah. Because there are ways to arrange so the way I think about covariance is that covariance is a measure of a linear relationship between x and y, right? So as a result, you can have x and y having a non-linear relationship, in which case they're not independent, right? But their linear relationship is 0, right? So the way to think about this is that we can come up with examples whereby x and y have a non-linear relationship, but they have a 0 linear relationship. So in that case, they will have a covariance of 0, but they're not independent. Okay. Yeah. Okay. Conditional expectation. Okay. So P of x and y, P of x given y is the conditional probability of x given y, right? So in particular, is this a distribution over x or distribution over y? Can y'all tell me? So this is a distribution over x. That's correct. Okay, and so we can talk about a conditional expectation with respect to this conditional distribution, right? So in conditional expectation, right, instead of a normal probability distribution, we have a P of x given y in here, right? So sum over x, f of x and y times P of x given y. So this is called the expected value of f of x and y given y. Okay. In the standard form, we write it as like this: expectation of f of x and y, and there's P of x given y here. So this P of x given y is to remind us that we are conditioning on P of x given y. Okay, the expectation is with respect to x given y. Oh, sorry, the triangle means is defined as. Yeah. Thank you for asking. Right. In general, all this notation here and this notation here are equivalent, but I prefer this notation here because we are making the expectation very explicit. In particular, we're saying that the expectation is with respect to P of x given y. Okay. So the conditional expectation tells us the average value of f of x and y, taking into account P of x given y. Okay. So this assumes x is discrete. If x is continuous, then we integrate over x. okay, instead of sum over x. So x is discrete here, x is continuous here, okay, right? Anyone have any questions before I do an example? Okay, example, right? So previously we've already computed p of x equals 0 given y equal -1, that's 1/3. And then we have computed all of this, okay, from previous time. So given that y is equal to -1, what is the expected value of x? Right? So we can plug in the formula. Remember, this is the formula from the previous page. But now f of x given y is x, and p of x given y is p of x given y equal -1. Okay. So again, this is a sum over x. X takes on two values, 0, 2.5. So there are two terms in the sum. So the first term is when x equal to 0 times p of x equal to 0 given y equal -1, plus the second term is when x equal to 2.5. So 2.5 times p of x equal to 2.5 given y equal -1. And so we can plug it in. P of x equals 0 given y equal -1 is 1/3. P of x equal 2.5 given y equal -1 is 2/3. We plug it in here. And the expected value of x given y equal -1 is 1.667. Okay, so basically after we observe y equal -1, the expected value of x actually went down compared with before. Okay, so it's lower than before. Okay. Questions, anyone? Questions? If not, let's take a 4 minutes break until 8:05. Okay. Okay, let's start again. I'll appreciate if y'all can turn on your video. Okay, let's do this. Last part. Hooray. Okay. Hopefully y'all are still hanging in there. The last part actually won't be an hour long, I promise. Yes, we will definitely end before 9. Okay. Yeah. Okay. So just now we talked about 1 random variable, 2 random variables. Now we're going to talk about n random variables. Okay. Okay. Oh, sorry, Nitin, I just saw the. Oh, I realized I missed a few questions. What does f of x and y stand for? Oh, I see. That was after the break. Okay, sorry. Sorry. Let's go with eating. Are you asking about this f of x and y? So this f of x and y is any function, right? So if you look here, f of x and y is any function of x and y. And in this example, f of x and y is equal to x. Does that answer your question, Ethan? And why does f of x and y is equal to x? Oh yeah, because in this question, I want to know the expected value of x given y is equal to -1, right? So if you look at this starting formula, oh, hold on. This starting formula here would already imply f of x and y is equal to f of x and y is equal to x. If you look here, inside this bracket, this is f of x and y, right? Does that answer your question? Cool. Nitin asked me to do the example for y equal -3. Let me think. Do I want to do that now or later? Nitin, why don't you ask me at the end of the class? Because yeah, can you ask me again at the end of the class? Okay, yeah, okay. Cool. All right, n random variables. Okay. So far we're talking about 2 random variables, right? X and Y. But in real application, there are usually more than 2 variables. A photo has 1 million pixel, right? There is like 1 billion Facebook users or whatever, right? So there are, in general, there are many random variables in most applications. Okay. So if we observe x1, x2 to xn multiple times, some combination of outcomes are going to be more likely than others. Okay. So this is captured by the joint probability distribution function. So P of x1, x2 to xn is, we read this as probability distribution of x1 to xn, right? So if x1, x2 to xn are continuous, then P refers to joint PDF. If x1, x2 to xn are discrete, then this refers to joint PMF, right? But sometimes some x are discrete, some x are continuous. So there's not really a name for it. So I'm just going to call it probability distribution. Okay, right? Okay, so many properties. The good news is that I think most of you should have covered up to 2 random variables in your undergrad. So hopefully only this part is somewhat new. And the nice thing is that many properties of 2 random variables generalize naturally to more random variables. Okay. So remember that we have P of x and y, right? So to get P of x, we integrate y to get P of x, right? So assuming y is continuous, we integrate y to get P of x. If x is continuous, we integrate with respect to x to get P of y, okay? Now, this works in higher dimension as well, right? So let's say we have P of w, x, y, z, right? Then let's say z is continuous, so we integrate with respect to z, and let's say w is discrete, so with some respect to w. So if we integrate with respect to z and some respect to w, we're left, if we integrate with respect to z and some with respect to w, we're left with only x and y, and so the left-hand side is P of x and y. Okay, is everything okay so far? Does this make sense? So the law of total probability and marginalization generally works for n random variables as well. Okay. Now, what about conditional probability, right? So for 2 variables, we say P of x and y is equal to P of x times P of y given x, right? So here's my trick for trying to remember this, right? we can think of this as the probability of observing X and Y is the same as the probability of observing X. Then after you observe X, given that you observe X, you observe Y. So that's why P of Y given X. Okay, so this is my trick. Okay, so with 3 random variables, you can do the same thing. P of A, B, and C is equal to P of A times P of B and C given A, right? So think of this as this. The probability of observing A, B, and C is the same as you first observe A, so probability of A. Then given that you have observed A, you observe B and C, right? So probability of B and C given you have observed A. Okay, and then we can repeat. So probability of B and C given A is the same as probability of B given A times probability of C given A and B, right? So because here, this is the probability of observing B and C after you have observed A, right? So then you first observe B. So probability of first observing B given A. Then after you observe B, you observe C, right? So probability of observing C given that you have already observed A and B. Okay, is everyone okay with this? Okay. So we can do this indefinitely. We can do this for n random variables, right? So P of x1 to xn is the same as P of x1 times P of x2 ... xn given x1, right? So this is saying P of x1 to xn is the same as we first observed x1, so P of x1 times the probability that of x2 given xn, given that we have already observed x1, correct? Right? So the next part is the same, right? So you can keep decomposing this as well. So we can decompose this. So we have x2 to xn here, right? So let's say we observe x2 first, right? So this becomes P of x2 given x1. You take x1 and you copy here, right? So now that you have observed x2, it needs to go behind here, right? So now you have observed x1 and x2, right? And so the remaining variables become x3 to xn, which we copy here, okay? Right? So to say it out loud, right? So the probability of observing x1 to xn is the same as first observing x1, so P of x1. And then given that we observe x1, we observe x2, so P of x2 given x1. Then given that we have observed x1 and x2, right? Given that we observe x1 and x2, we observe x3 to xn. So P of x3 to xn given x1 to x2. Okay, and you can keep doing this. So if you do it n times, you get this, right? P of x1 times P of x2 given x1 times P of x3 given x1 and x2 ... times P of xn given x1 to xn minus 1. Okay, is everyone okay with this trick of remembering? Okay, cool. Now, this is the part whereby some of the stuff doesn't quite apply here, independence, right? So remember when two variables are independent, then x tells us nothing about y tells us nothing about x, right? So when there are n random variables, it becomes a bit trickier. So we say that x1 to xn are independent if knowing any subset of x tell us nothing about the remaining x, right? So if you know x1 and x2, it doesn't tell us about the remaining variables. If you know x3, x4, x5, it doesn't tell us about the remaining variables, right? No matter which subset of x you look at, it tells us nothing about the remaining subset. Okay. And so if x1 to xn are independent, right, then we can actually take that joint distribution P of x1 to xn. And again, we can write it as P of x1 times P of x2 ... P of xn. Okay. And then this is equal to product from small n equal 1 to capital M P of xn. Okay. So this is an if and only if statement, right? This means that if I tell you the joint distribution can be written in this form, right? Then this means that x1 to xn are independent. Okay. So there's another common concept, which is independent and identically distributed, right? So if x1 to xn are independently and identically distributed, then this means that they're independent and they have the same marginal distribution, right? So let's say they're all Gaussians. Okay, does it make sense? Okay. Does anyone have any questions so far? Does the distribution have to be the same in the last case? Yes, yes. Yes, they follow the same distribution. Yes. That's why they are say identically distributed. Yeah. Okay. Now, this is the last set of stuff we're going to talk about, which is conditional independence. Okay. So there's a new concept called conditional independence when you have more than 2 random variables, right? So most of you probably have not seen this before unless you took my undergrad course. Okay. So x1 and x2 are conditionally independent given x3. If knowing x3, sorry, hold on. If we already know x3, then x2 tells nothing about x1 and x1 tells nothing about x2. Okay. So we say that x1 and x2 are conditionally independent given x3, right? And we can write this formula, P of x1 and x2 given x3. Because given x3, they're independent, therefore we can write it as P of x1 given x3 times P of x2 given x3, right? Okay. Anybody has any question about this concept? Okay. So now, if x1 and x2 are independent, then it does not imply that x1 and x2 are conditionally independent given x3, right? Basically, even at first, x1 and x2 are independent, but if we know a new random variable x3, then x1 and x2 might no longer be independent. Okay, so for example, let x be equal to 1 if Thomas comes to class wet and then 0 otherwise, right? Then let y be equal to 1 if raining, 0 otherwise. Okay, so then let's say z is equal to 1 if Thomas is involved in a water fight and 0 otherwise. Okay, then let's say y and z are independent. For example, let's say whether it's raining or whether I'm involved in a water fight, they're independent, right? But after we know x, then y and z are no longer independent, right? And the reason is that we assume that, let's say there's only 2 reasons why I can get wet, either from a water fight or from a rain, right? So then suppose I come to class wet, then knowing it's not raining would suggest that I was in a water fight, right? Because if I come to class wet, then if it's not raining, then that means I was involved in the water fight. And so this would be an example whereby even though x1 and x2 are independent, but given x3, they're no longer independent. Okay. I guess, is everyone okay with this? Any questions? Another less frivolous example may be like, for example, let's say I'm making up, but let's say there are lung cancer. Let's say there are only 2 reasons why you might get lung cancer: smoking or you work in a coal mine, right? So then if, let's say, I know if someone has lung cancer, right, and the person does not smoke, then we would infer that the person works in a coal mine, right? Does it make sense? So even though smoking and working in a coal mine, they might be independent, right? But after you know that the person has lung cancer, then they are no longer independent. Okay. Any questions about this? Okay. Right. Okay. So special case 2, right? If x1 and x2 are conditionally independent given x3, it does not imply that x1 and x2 are independent. Okay. So you might have 2 random variables. If you know a 3rd random variable, they're independent, right? But it does not mean that without x3, they're independent as well. Okay. So for example, let's say if I toss a coin 99 times, and q is the probability of getting a hit, and xn is equal to 1 if the nth coin toss is a hit, and xn is equal to 0 if the nth coin toss is a tail. Okay. Then in this example, x1, x2 to x99 are independent, conditioned on knowing q, right? Let's say I tell you q is 0.7, right? Then if I tell you q is 0.7 and you believe me, right, then x1 to x99 are independent, right? But if q is not known, then x1 to x99 are not independent, right? So imagine if you don't know q and you toss the coin 99 times and they're all equal to hit, right? then what would you guess the 100th coin toss? Would you guess hit? Right. Yeah, I think most people guess hit, right? And that's because not knowing Q, right? The coin tosses are not actually independent, because the observation of the 99 coin toss actually give us information about Q. And by telling us some information about Q, it informs us about the 100th coin toss. Okay. So this is probably confusing because in your previous statistics class, right, you might have seen this, right? Probability of hit, tail is equal to Q squared times 1 minus Q, right? But actually in your previous probability class, well, okay, so first of all, this is not exactly right because Q is appearing on the right-hand side, but not on the left-hand side, right? So actually what is happening is that in your previous class, they might not have shown it more explicitly because to avoid clutter, right? So the proper way to write this probability of hit, tail is given Q is equal to Q squared times 1 minus Q, right? So a lot in your previous course, this given Q might be implicit and they often drop it to reduce clutter. Okay. Does anyone have any questions so far? Okay, so okay, so what? Oh, sorry, hit HHT is hit tail. Hit tail. Yeah. So in your previous class, in your previous probability class, there's probably a lot of coin tossing, right? I think most undergrad probability class have a lot of coin tossing. So you might get this, what's the probability of observing hit and tail, right? Then it would be like Q squared 1 minus Q, right? Okay. Okay, great. So why Q matters since Q is constant? Even though Q is a constant, you're saying, sorry, you want to elaborate a bit more, Liu Chen. You're saying that if Q is a constant, why does it matter? Because Q is the probability of getting a hit in the coin toss, right? The probability of getting a hit for the coin toss. So therefore if Q is equal to 1, then every coin toss is going to be a hit. If Q is 0, every coin toss is going to be a tail. So that's why the value, knowing Q or not, is very important. So because, for example, if you observe 99 coin tosses, they all hit, you will probably infer that Q might be close to 1, right? And so you would guess that the 100th coin toss is hit because Q is probably close to 1. Does that answer your question, Liu Chen? Cool. Okay. So before we end, let's do a quick thing. Oh, I see. I told you before 9. Even we're gonna end before 8:30. Okay. All right. So I'm gonna try this thing with you, whereby you can download this app or Poll Everywhere app, or you can just type this pollev.com/thomas0005 in your browser, and then we can try this question. Okay. So yeah, as you can see, you can. Oh, let me see if it's working. Is it working? I think it's working. Yes. Okay. So which algorithm is better? Algorithm A, the accuracy and training set is 80%, and the accuracy and test set is 80%. And then algorithm B, the training accuracy is 95%, and the test accuracy is 80%. Oh, you can answer in the if you go to the website, you can answer. You don't need to answer in the chat. Go to poll, like Iwi has already posted the link. If you click on the link, you can answer. Yeah, it's anonymous. I won't know your answer. Yeah. So yeah, so you all can go to this link. You actually don't need to answer on the. You can go to this link. Okay. Oh, still people trying. Okay, I think we're 152, 154. Is anyone still trying or? Okay, well, every time I say okay, the numbers goes up. I'm not expecting, yeah, okay. There are also some people who are changing their mind, apparently. So, oh, yeah, okay. Have we converged? Yes. No. Okay, yeah, okay. So roughly speaking, most people choose A. The second most popular choice is no difference. Actually, okay. I think that if we care about test set accuracy, which we mostly do, then actually it's no difference because they both have 80% accuracy. Okay, right? So it's true that algorithm A has so-called less overfitting and algorithm B has more overfitting, but ultimately, let's say when you want to apply on a new data set, right? You do care about the test set accuracy. So I would say it's no difference. Okay. Okay. So there's no point changing your answer now. You're not graded. Yeah. And I also don't know who answered. So yeah. Okay. All right. Okay. So so to summarize, we talk about discrete and continuous random variable. We talk about probability distribution function and probability mass function, joint distribution and random variable. We talk about marginalization and law of total probability. We talk about conditional probability and Bayes rule. We talk about independence and conditional independence. And then we talk about expectation and conditional expectation. So by right, you should know most of this except maybe the n random variable portion. If you find that you do not know most of this, then I'm actually quite worried about whether you can handle the course. At least for the first half of this course, the 5907, the first half of 5907 and the 5027, I do assume you have really good grasp of your probability and statistics. So yeah. So you should try to evaluate yourself to see if today's material was easy or not, right? And you might want to try out the problems for this week to also get a sense of whether it's easy or not. Okay. So these notes are from chapter 2 and 3 of the computer vision textbook. This one is free download. I hope it's still free. The last time I checked was free. So I can point you to it. For the other online version, you can look for it yourself. Yeah. Okay. I have also uploaded some review of probability and linear algebra by Dr. Tam. Yeah, anyway, so that's it. So that's all I have for today. Does anyone have any further question? How about I answer the question from Nitin, who's still here? He wanted me to do that example. Let me share screen again. Oops. He wanted me to do what was it again? I think he wanted me to do, which question you wanted me to do again? Probability of, the recording will be uploaded. Yes, this is the one. And then you want me to do for which one? Y equal -3 or something, is that right? Okay, so y equal -3. Yeah, sure. So let's do it. So let's think about this. I can do this. So probability, expectation of p of x given y equal -3. The expected value of x given that y is equal to -3 is equal to, so actually we can actually steal some of this equation here, right? So it's the same equation as here, but now you just replace y equal to -3. So now this is sum over x, p of x given y equal, oh, sorry, -3. Okay, you can see that this is the same. What happens if I do this? Does that work? Oh, it works. Okay, yeah, okay. This is the same formula as here, right? Except that now is y equal -3. Okay. So then I can plug in, right? So again, x can take on two values, 0 or 2.5, right? So when x is equal to 0, p of x equal to 0, given y equal -3, plus when x is equal to 2.5, right? X can be 2.5. So 2.5, p of x equal 2.5, given y equal -3. Okay. So this is 0. So this is still 0. So p of x equals 0, given y equal -3. Oh, I see. Hold on. Oh, okay. It's not going to be easy for me to do because we have not pre-calculated this. Yeah. How badly do you need me to do it? Or do you get the idea now? Because we didn't pre-calculate this, so I will need to pre-calculate this as well. Nitin, how do you want me to do it, or you're fine now? Okay, cool. Yeah. So then you have to recompute this for when y equal -3, and then you can plug it into this formula here, right? And then you get the answer. Okay. Cool. How? Any more questions for anyone?
Hi, Prof.
Yes.
So can I just check, right, for the question that you just did, right? What if fxy is not x? Instead, it's like xy. What would the notation look like?
Oh, I should. Sorry, 1 second. Actually, I stop sharing. So you're saying that what is the expected value of
xy given x equals to something?
Sure. So let's say expected value of, let's say this example again, right? Given like this, right?
Yeah.
So the thing is, in this case, like y, we already know y equal -3, right? So then this is expectation of, so this is equal to sum. This would simply be sum over x times y, but in this case, we know that it's -3, right?
Okay.
P of x given y equal -3, right?
Okay,
and so essentially, it will be the same as this, except you have an extra -3. Yeah.
Okay, if it's like x squared, then the px is still like px by alone, it's not x squared given y equals.
Oh yeah. Oh, I see. Very good point. You're saying that if this is x squared, is it? If this is x squared, then we only need to square this. This x remains the same.
Okay.
Then this becomes square. This becomes square. Yes.
Okay. Okay. Thanks.
Right. Because if you look at the formula, if you look at this formula, right, it's always p of x given y, right? You don't square this. If f of x and y can be x cubed, x to the power of whatever, and this would still be the same, right? Yeah.
Okay. Okay. So the so-called px given y thing is just saying that we are using the x across given some particular y lah. And
yes.
It's not like the function.
Yes.
Okay.
Think of it as yeah. So if you look at right. So for, let's say for this example, this is saying that like, oh, let's say you observe y equal -3, right? Then you sample x given that y equal -3, and then you compute the x square based on the x, and then you repeat it many times. On average, what's the value of x squared? Yeah.
Okay.
Right. So you're still sampling from x, you see? Yeah, because this is the distribution of x given y. Yeah.
Okay. Cool. Thanks.
Okay. Anybody else?
Hi, Prof.
Yes.
Actually, I have two questions. The
Yes.
first one is about the validation. So you mentioned that if you want to test, maybe compare 3 algorithms, and by using the training, validation, and testing set, and just fix the test set, and we just try to validate if which algorithm is the best. Then maybe in the end we got maybe algo 1 is the best, and we test on the test set. Then would it be possible that actually algo 2 is better than algo 1 on the test set? And if it is so, shall we change it into algo 2?
By right, you wouldn't know because you're not supposed to test your algo 2 in your test set, right? So you wouldn't have known at all. Yes. But you're right. I mean, there's an unlimited amount of testing you can do, right? Presumably in like real world system, you're constantly testing and making sure that your algorithm is not going haywire. And if it's bad, you need to go in and see what's going on. Yeah.
Because I'm thinking if we want to compare between like with others, and which way is the fairest way to do, because maybe everyone will have a different test set, then there might be difficult.
Well, if everyone has a different test set, I mean, that will of course happen, right? In the sense that, for example, imagine that you develop some machine learning algorithm for some medical application, right? So, and then you want to start to some other country. Then your applications might be developed, let's say in Singapore, and then it may not apply to other populations as well. So this is why you need more testing. Let's say when you try to deploy your algorithm to different location. Yeah.
Okay, understand.
There's no magic way of getting around it, I think. Yeah.
Okay, sure. And another question is about the curse of dimensionality. And about that, dimensionality is the number of features, right?
It can be the number of features. It can also refer to the number of parameters in your model.
Okay, then if it's the number of features, can I say that it's because of maybe some of the features is very hard for the classifier to differentiate which feature is belong to which class, and that might result in a confusion in the end.
Yes.
By combining them.
If you have a lot of features, basically they're uninformative, that tells you nothing about the classes. Let's say you're trying to classify, then it might confuse the algorithm. Yes. Yeah.
Okay. Thanks.
Eating is asking, uploading for lecture recording will be under the conference tab, right? I think so. Yes, I think so.
Hi, Prof.
Yes.
Sorry, this may be a less relevant question, but for the Bernoulli distribution, right, that you shared earlier, is there a reason why we choose to take the exponent instead of multiplying? So, for example, right, so probability of x is lambda to the power of x times 1 minus lambda to the power of 1 minus x, right? It will give the exact same result if we did like probability of x equals to x multiplied by lambda plus 1 minus x multiplied by 1 minus lambda.
So I say that again, it will be equivalent to what?
X times lambda plus 1 minus lambda times 1 minus x. Is it like some special nice thing?
You are actually right. That might also work as well. Yeah. Yeah, actually good one. Yeah. But would it work for the categorical distribution as well?
Yeah, I think it will just change to a summation.
No, but then you can no longer do 1 minus x, right? It wouldn't work, right? Would it? Oh, I see. Then you can use the one hot encoding. I see.
Yeah, you choose it by the same way.
I guess I'm actually not sure, but one reason might be a lot of time when you're trying to optimize this kind of stuff, you need to take the log. And so in the product form, the log is easier to deal with, right? Because when you do log of a product xi, it becomes sum of log xi. So that might be one reason. Yeah.
Okay.
Right. With your form, if you try to take the log, you're stuck actually. Yeah.
Yeah. Okay.
Right.
Cool.
Yeah.
Thanks.
Yes. I guess this will be the when I use this kind of stuff, I guess if I use your form, I'll get stuck when I'm trying to when I try to do this. Yeah, when I try to do the law. Yeah. Yes. Good question.
Thanks.
Ling Ming is saying why 95 accuracy in training set means overfitting, or 95% accuracy means that it's more likely to overfit. Oh no, that's not true. So in this case, overfitting refers to the gap between the training set and the test set. Yeah. So if your training set is 95% accuracy, your test set is also 95% accuracy, then there's no overfitting, right? And you're doing fine. Great. You're doing great. Yeah. Does that answer your question, Ling? Huh? Any more? For K-fold cross-validation, can we simply average across all test set to compute the test accuracy? Yes, the people typically average across all test set. Very good. Since the overlap in the training data and test accuracy are not independent. This is very good. So if we are reporting the average, you can average across the test set. When you're doing statistical tests, actually in machine learning, for some reason, most people don't do statistical tests. But in applied areas like mine area, we do statistical tests to show that one algorithm is better than the other. So in those cases, yes, you do need to take into account that the folds are actually not independent because of the overlap in training set. And so in junction, so in my group, we typically use, for example, the resample t-test. Yeah, anyway, it's not part of the, it's only for those interested. You can look up this resample corrected t-test. Yeah. It tries to correct for, it's from a Banjo 2004 paper or something, where it tries to correct for the overlap in the training set. Yeah. But average is fine, right? Actually, average is very robust to non-independence because the expected value of two random variables, if you sum two random variable, expected value of x plus y is equal to expected value of x plus expected value of y, even when they are, hold on, now I'm confusing myself. Even when they're not independent, right? Even when they're not independent, right? So some reason it's only, my breaks down. Yes, yeah. So yeah, expectation works, yeah. You're right. It's variance that doesn't work. So when you're averaging accuracy, it's fine, they're not independence. Yeah. Any other questions? Uses the categorical cross entropy loss. This is a log version of the categorical distribution. Actually, I don't remember what's the formula of the categorical cross entropy loss. Junction, do you remember? If you're still here. Yeah, sorry, I would need to look that up. What the formula looks like. It could be, yeah, categorical cross entropy. Cross entropy loss. I thought it was something different. Doesn't the cross entropy loss have some? Does it not have some exponential? Or did I? Yeah, I thought it's some exponential log, right? Maybe I remember wrongly. Yeah, so it's not exactly the same, right? Yeah, it's not exactly the same. No, so it's not exactly the same. Yeah. Okay. Yes. Any other questions?
Hi, Professor. I would like to ask questions about the page training validation test sets. Yes. You said that you can repeat as many times as we like in the validation test, is it right? I was wondering if you say repeat as many times as we like in the validation test, will the validation test
sorry, in the validation set, you can repeat as many times as you want a validation set.
Yeah, I'm sorry.
Not the test set. You don't want to touch the test set. Yes.
Yeah, in the you repeat so many times in the validation set, or will this validation set becomes, you know, in a form like a training set, because you have already just validate so many times there. It is like a training. It's like training on this set.
Right. So there's actually a risk that if you use a validation set too much, then when your algorithm finally works very well in your validation set and you try on test set, then you realize that it actually does not work that well.
Yeah. So in this case,
so that's a risk.
I mean, in this case, there's no meaning to using a validation test as you repeated on it. So
yes. But the whole point of what I mean is that, but at least now when you apply the test set, you will still be able to catch that you actually overfitted to the validation set, right? Because you only use your test set at the end. Yeah. So yes, your algorithm still sucks, but at least you know your algorithm sucks. That's my point. Yes.
Oh, okay.
Yeah.
And the key fold cross validation, and
yes.
I have the do you mean that every time we select one of these fold, we apply a brand new algorithm with the whole with a whole different set of parameters?
Right, in the K4 cross validation, yes, you typically would so let's say in the first round where this is the test set and the remaining are the training set, then you would actually you estimate your model parameters here, and then you test here. And then when, let's say this is a test set and these two are the training set, then you would re-estimate your model parameters in this two training set, and then you test here. So you're right, in each case, the parameters are different.
Each case parameters are different.
The model parameters are different. So this is why Christopher, I think just now was asking, then after you've done your K4 cross validation and you like an algorithm, how do you apply to new data, right? But because each for your model parameters are different. So then what you can do is that you can retrain over the entire data set if you want, right? So you get one final model to apply to a new data set. Yeah.
Okay.
Does that answer your question?
Okay. Yeah. I just want to make sure. I thought it was using the same algorithms, and I think that there will be overlaps because say if you apply the first fold in the first time, and the first fold as the test set, and next time you select the other fold, but in this time the previous test set will become the training set of the next stage, so there will be overlap. So in this
that
case,
is okay. Sorry, just to clarify, right? You're typically, okay, sorry. The most common way people use this cross validation is that let's say you have one algorithm and you don't have enough data and you just want to test it, right? Just to clarify, it's the same algorithm, but the parameters are different, right? So let's say it's a neural network, right? And then you have some parameters you need to train from the neural network, right?
Yeah.
So the neural network architecture might be the same across these folds, but the parameters are different. You have to retrain the model each time.
Okay. I got you. You mean the algorithm are the same, like just for example, like the structure or the initial parameters are all the same, but say every time you select each fold, you will use the same set. For example, the initial parameters and the same structures. In this case, I will use this, for example, the first fold as the test set, and the next time you use the same algorithm, but the parameters will still be the initial parameters. it will not say using the outcome of the first stage parameters.
No. You shouldn't use the first round parameters.
Yeah.
Cheating. Yes.
Yes.
Yes,
So we'll just use the we'll just use the in the second stage we'll use we'll also use the initial parameters and the same structure.
And then you repeat your training from scratch. Yeah.
Okay, I get it. Okay, thank you so much.
Yeah. Okay, good. Max comment is taken. I think we've clarified that. On page 198. Okay, let's go to page 198. Page 198. Okay, I can share screen. In page 198, the P is from the 99 times, right? Sorry, what P are you talking about? Is there a P here? I missed that. You mean the Q? What? What's the P? Oh, you mean here? You mean this P? Chen Guan, you want to tell me which part you're talking about?
Sorry, it is the Q.
Oh, you mean the Q? Yes, what about the Q?
Yeah, I'm not.
Why is it not independent if we don't know Q? Yeah, that's always tricky. So if we don't know Q, the reason why X1 to X99 are not independent is that if you know X1 to X98 are all hit, right? Then it tells something about Q, which in turn tells something about X99. Does that make sense?
Sorry.
So sorry, 1 second. So knowing X1 to X98, right?
Yeah.
It tells us something about Q, which tells us something about X99. Does that make sense?
Yeah.
Yeah, so that's why it's not. So that's why the X1 to X99 are not independent. If we don't know Q. Yeah. Okay. Okay, so any more? If not, we're good. Should I just, okay, I'm gonna count to 10 and then we're gonna hang up. Okay, last chance. 10, 9, 8, 7, 6, 5, 4, 3. You can of course email me. 2, 1. Yes. Okay.
Hi, Prof.
Oh, wow. Very good. You guessed me one last time. Okay, good. Go on.
So I'd like to know if the Q is from the last 99 times.
Sorry, say that again.
So I don't know what the Q means. So if
Q.
Yeah.
Q is the probability of getting a hit. I see. Q is the probability of the coin turning up as hit.
So it is from the 99 times before, right?
Pardon? Think of Q as some intrinsic property of the coin, right? If I give you this coin, right, it has some intrinsic property, right? Correct. Does that make sense?
Okay. Yeah.
So Q is some intrinsic property of the coin. Like you could imagine that they might, actually I don't know how to make a coin which is like unfair. So maybe they load one side of the coin such that it's more likely to turn up head or turn up tail, right? So it's an intrinsic property of the coin. Does that make sense?
Yeah. Thank you.
It's some fundamental property of the coin, yeah, that we cannot change, right? Sijia is asking, is it because if Q equals 0, they will no longer... Actually, no, it doesn't matter whether Q is 0 or not. Like, you can also imagine that like Q is 0.5, right? In which case, when you observe X1 to X99, you know that, and then half of the time is coin head, half of the time is tail, right? So if Q is, the true value of Q is 0.5, then if you look at X1 to X99, roughly half will be head, roughly half will be tail, right? Then, so this will inform you that Q is maybe around 0.5, right? You might not know the exact value of Q, but you now know that, okay, Q is maybe around 0.5, right? In which case, you will guess the 100th coin toss, you would say that the 100th coin toss has a 0.5 probability of a hit and 0.5 probability of tail, something like that. Does that answer your question, Jia?
But I think if it is what you said, what you mean is X1, X2, X to X99, they are say apparently the probability is probably say half, but the relationship between this are still independent, you know, because for example, you toss the coins for the first time, and the second time you toss this coin, the result of the first time does not have any impact on the second result. So there are still independent.
Only if you don't know, only if you know Q.
Okay.
Only if you condition on Q. Like here, if you condition, oh, sorry. If you condition on Q, then you can write Q square 1 minus Q. If you don't condition on Q, you cannot do that. Yeah.
Okay, I think
Yeah, you think about this.
later.
Yes.
Yeah.
Yes.
Thank you.
Yes. Chenri is asking for the assignment we upload. Do we need to submit it? No, you don't need to submit it. Edin is asking if we don't know Q, then it might be from the X1, X2 to X98 when we make the 99th test. Right. Actually, okay. Sometimes explaining more might be easier than explaining less. So the way I would do this is that, okay. Let me tell you, like, okay, so I don't know if this will help or confuse you further, right? But actually next week we'll be doing some of this, right? So let's say probability of X, probability of X 100 given X1 to X99, right? I'm claiming that it is not equal to Q. The proper way to do this is that probability of X1, oh, sorry, the probability that is equal to 1, ahead, okay? So probability of X1 given X1 to X99 is actually equal to, this is a bit nasty, okay? The way you would do it is that you need to introduce Q, P of X 100 equal 1, and Q, X1 dot 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 X99 dQ. Okay, so this is the law of total probability. Everyone agree with that, right? Okay, right? And then after that, you can then say P of Q given X1 dot 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 X99, right? Times P of X100 equal 1 given Q and X1 to X99. Okay, dQ. Okay, right? So this is the conditional probability. We're saying that the probability of the 100 coin toss being hit and Q given X1 to X99 is probability of Q given X1 to X99 times probability that X100 is equal to 1 given Q and X1 to X99. Okay. And so now condition on Q, then X100 is now truly independent of X199. Okay. And so this is P of Q, X1 dot 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 to X99 times Q, right? Q is the probability of it. This is Q dQ. Okay. So actually, so this is exactly how the previous coin toss will influence the future coin toss, right? In the sense that you can see that actually, imagine if all this 99 coin tosses are hit, right? then this distribution is going to look something like, it's going to look something like this, 0, 1. This is Q. Then this distribution will probably look something like this, right? Does that make sense? Oh, sorry. Correct. And so when you integrate over, you will realize that the probability, like if all these coins are hit, then the probability that the X100 equal to 1 will be quite high. Okay, much bigger than 0.5. I guess next week you'll see. It depends on the prior that you said. Okay, right? If let's say all of these are like, half of these are like, 50% hit, 50% tail, right? Then this distribution might look something like this, right? 0, 1, Q, and then your distribution might look, I don't know, something like this. Okay, right? Around 0.5, right? Okay. Then from here you might conclude that, oh yeah, this distribution, the probability that the next coin toss is 1, it might be around 0.5 or something like that. Does that kind of make sense? Yes, Max is right. Q will be affected by each of the coin toss when Q is unknown, right? Through this exact mechanism, right? Knowing the previous coin toss inform you about Q. So Q has a new posterior distribution, right? Yeah. I think, okay, I was looking to see if there's any new messages. Does that help you a bit? Or it just makes things more complicated? So sometimes more math helps, sometimes more math makes things more complicated. Oh, okay. So sometimes more math helps. Yeah. Yeah. Okay. Yeah. Okay. Anyway, cool. So, okay. So we're gonna count down again. All right. Okay. 10. Oh, okay. Good. Shengguan, I'm glad it helps you. 9, 8, 7, 6, 5, 4, 3. Now I'm very afraid of going to 1. Someone's gonna ask a question at 1, 2, 1. Okay, good night, everyone. Yeah. Bye, Paul. Bye.